Okay, thanks a lot. So hello, everyone. I'm very happy that the EDBT organizers have given me the opportunity to talk to you about this line of research on probabilistic databases. So today I'll start with an introduction of the motivations of why we think it's a relevant problem. So for the practically oriented among you, I don't know if any people joined from track 2 or something like that. I will try to give practical motivations. But I think you'll pretty much quickly realize that what interests me personally in this is more the theoretical aspect than the practical aspect. There have been other talks like this in the school before. And then I will present the models of probabilistic databases and the computational complexity results we have about them. Feel free to interrupt at any time if you have questions. I have prepared, I think, way too much material, so I'll cover what I can. Don't worry about slowing me down. It's probably a good idea. Okay, so why do we need probabilistic databases? It's because we have uncertain data everywhere in lots of applications. So you can think about data that has been automatically extracted, data that has been annotated by some machine learning system, giving confidence values to things. You can think about data which is wrong in the first place. You can think about fake news. You can think about vagueness. You can think about measurement errors. There are lots of application cases where the data that you have is not correct, is not exactly correct, and where nevertheless you have this data and you'd like to reason with it. And probabilistic databases are a way to handle this uncertainty and try to do something with it, if possible, in a principled fashion. So I'll start with reviewing some use cases, well, not really use cases of probabilistic databases per se, but cases where uncertainty appears in applications, focusing on research projects. So this is, for example, the never-ending language learning project at CMU that has been running for several years. This is a project that crawls, so reads the web, which means they crawl the web and they try to extract structured facts out of it, of the form something is something else. I mean, other people are doing this. I expect that Google is also doing this to provide instant answers when you do searches. But this is a research project, so we know better how it works. And you can see that the extracted facts, so since they're extracted by an automated system, they have a confidence score, and people on the website can even vote for or against the fact, which I imagine is reflected in the confidence score. So if you were to use this data to answer queries, for example, it would probably be a good idea to take these scores into account, and the question is, how would you do that? Another use case like this is the Yago knowledge base. So this is developed by Fabian Suciu and others at my team in Télécom Paris. So the current version of Yago is based directly on Wikidata, but the older versions were constructed by extracting facts from Wikipedia articles in an automated process that could introduce errors in the extraction. And for this reason, the facts had a confidence score. So the way they did it is that they simply did a kind of user study where people manually checked a sample of facts, and they used this to give confidence values to predicates. Again, these values are something that we'd like to handle when answering queries using Yago, but how could we do it? This is an example of a research project that used to be called GeoDeepDive. This was a project of extracting structured information out of scientific articles. So here in the geology domain. So from an article, you first need to do OCR if you don't have the text to get the text. Then you need to do some kind of NLP analysis to parse the text. And then you need to do some kind of information extraction to get structured facts out of it, mapping it to a table and such. Each of the steps in this process can introduce some uncertainty and add some errors. And the question is, how do you manage these errors throughout the pipeline? Another use case again, crowdsourcing. Don't know if you're familiar with crowdsourcing. So this is not crowdfunding, right? This is it's the reverse. You pay the crowd instead of getting money from them. This is a system where you can ask users to answer simple tasks that computers don't do that well, and you pay them a small amount of money per answer. You can use this to label data sets, to do some transcription of things, and so on. The result that you get out of these kind of platforms, so without getting into the ethical considerations of whether these platforms should exist in the first place, assuming they exist and that you use them, you get imperfect answers out of them, and you'd like to reflect this uncertainty in your data. Completely different application domain. Speech recognition and OCR system are based, or used to be based, on this kind of things. These are lattices that represent several possible decoding outputs. with probabilities and symbols. And basically, this is a concise representation of all possible decodings, all possible ways to transcribe the text that you have seen in an image or heard. And so several possible decodings are represented concisely by this kind of lattice diagram. And so if the output of your decoding is this, how do you reason with it? So from these examples, I hope you can already see that uncertainty is something that's a bit complicated to characterize. You can have qualitative uncertainty in the sense of like missing facts, missing values, or quantitative, where you have a confidence score, or ideally you have a probability, so some kind of normalized probability value. I'm saying this to give you the broader context, and the rest of the talk will be almost exclusively focusing on probabilities that are numerical and normalized, because these are easier to deal with to prove some theorems and such. And there are several different possible ways that uncertainty can appear. So a value can be missing, a fact can be potentially incorrect. You can have alternatives between several possible values or several possible facts. You can have values that are numerically imprecise. So facts that can be wrong as a correct or wrong as a whole, uncertainty about the schema, data which might be missing, and so on. So again, this is this looks extremely intimidating, but we will be focusing on only a small subset of all of that stuff. So how do people deal with uncertainty currently? So I want to argue the uncertainty is here no matter whether you like it or not, right? Data is uncertain and you have to deal with it. And the way people deal with it mostly is to forget about it. So you have data, you know it's not correct, but you just pretend it's correct, and then maybe you have errors, and that's life. That's the worst possible way to deal with uncertainty, of course, if you want to think about it. The second worst possible way is to do some thresholding. So you have data like the Yago data with confidence scores, and you say, well, let's fix a threshold, 95%. Everything above 95% is completely correct. Everything above, everything under 95% is completely incorrect, and you just discard it. So this is like if you think about confidence scores, this is usually what happens. But if you have a process where you have several steps in succession, it could be the case that something which is less certain in the beginning becomes more certain as you go forward in the process. And if you just discard the uncertain stuff at each step, you're losing on precision as opposed to taking into account uncertainty in a global fashion, right? So we'd like a more principled way to process uncertainty throughout a pipeline. So here I will only talk about answering queries, so I won't really talk about OCR or any of that stuff. So this is what we would want, and I'm going to explain to you well, theoretical musings that are somewhat related to getting there. So I think it also leads to questions that are theoretically interesting for their own sake. And in the tutorial, I will be introducing stuff like tree width if I have time, circuit classes, and things like that, which are interesting not only for this uncertainty business. Okay. So I want to give you a vague overview of where we're going before. So you'll see the specific story is, I think, much more approachable. But the fundamental insight when we work with uncertain and probabilistic data is that we will have a concise representation of a set of possibilities or of a probability distribution over the possibilities. So the possibilities, the outcomes, in a sense, I call them possible worlds. So a possible world, so if you have data, which is uncertain, a possible world of the data is a normal database relation, which is the true state of the world, or that can be the true state of the world. And the idea is that since you have uncertainty, you have several different possible worlds, and you don't know which one is the correct one. And then if I talk about an uncertain database, it means a set of possible worlds. So I have the set, I think about the set of all the possible states of my data, but I'm not going to write down this set explicitly. Like if you think about, I have a database and every fact can be either true or false, I could write down all possible subsets, but I don't want to explicitly write down the subsets, right? I want to have a concise way to represent the subsets. So if I have a database table, I can say, let me think about all possible subsets, and this is an uncertain database. It's a concise representation of the set of all of its subsets, okay? And a probabilistic database is the same thing, except I also have a probability distribution over these outcomes. And the probability distribution can be over finitely many outcomes or an infinite set of outcomes. I'm just saying that this is possible, that it exists, but it's complicated, so I won't refer to it further. I will only talk really about finite sets of outcomes. And to demystify all of this a little bit, this is going to be an example of a probabilistic database in the simplest possible setting, tuple-independent databases. You see that this is just a standard relational table where I have annotated every row with a probability value like this. And into this fact has 0.9 probability of existing, this 1.8, this 1.7. And I think of this as representing the possible worlds that are all of the subsets with a probability value that's given by the independent choices according to these probabilities. So you see, this is easy to write, but it stands for an exponential set of possible worlds that are all of the subsets with probability values that are given by the product distribution. So if all of this confuses you, so just think about this and you can probably manipulate this without really understanding what's above. But if you can, get acquainted with the idea that we want to have a set of possibilities and we don't want to write it down explicitly, but we want to manipulate it with something that represents it. Oops, I don't know how I did that. I hope it doesn't matter. Well, I don't have any sound to play, so I guess that's okay. Right? So this is the roadmap of what I'll be talking to you about today. I will first present to you probabilistic databases, so the simplest possible model, tuple-independent databases. And then for completeness, I'll show you two other models that are far less used, but I think it's interesting that you see other possibilities of ways to define things, although I won't be proving any results about them. Then I will introduce to you the task of probabilistic query evaluation. So this is the central problem in the probabilistic database research. It's evaluating queries over the databases. So if you have a relational database and you want to evaluate a query over it, that's a pretty well understood problem. At least I hope you're a bit familiar with that. But now that we have these probability values in the way, it's not clear what we're going to do. And then I will show you results about the computational complexity of this task in data complexity. So there's a dichotomy shown by Dalvi and Suciu in 2007 and then extended in 2012 on conjunctive queries and unions of conjunctive queries that basically tell you some queries you can evaluate on probabilistic databases and compute the probability of their answers pretty much. And others, it's intractable to do that. And it's a dichotomy, so it's either one or the other. So I will prove to you this result in a very simplified case, and then I will hint at the fact that there are more complicated things going on. And then I will explain how we can understand the tractability result of this dichotomy in terms of restricted circuit classes from knowledge compilation. So this isn't going to give us any new complexity results. It's the same complexity result as above, but it's a different way to see it that has these connections to these circuit classes. And it has applications in terms of doing other things. So these circuit classes are also interesting for enumeration, for instance, thinking about Nico's talk. And they connect to a nice open problem. So I also want to mention that. And then if I have time, I'll talk about other approaches for tractability based on restricting the structure of the data. And then I have a bunch of other topics that I can talk about if time permits. Okay, good. So let's start. Yes. Very much. That's very true. So I mean, it seems related to provenance, and there are two ways to think about it. One is correct, and the other one is wrong. The wrong way to think about it would be to say, let me think about. So okay, this is wrong, and do not do that. But you could think there's a semi-ring of probability values, and we're going to multiply the probabilities and sum the probabilities. This does not work because when you multiply probabilities, if they do not stand for independent events, you're missing correlations and your results are not correct. So, I mean, a way to remember this is if you could have a semi-ring of probability values that's just about multiplication and addition, then everything would be tractable always. It would be p-time doable in p-time. And I'm going to show that it's sharply hard, so this isn't supposed to happen. But there is a real connection to provenance, and the real one is, let's think about these as Boolean variables. Let's compute the Boolean provenance. The provenance is a Boolean expression of these variables. And then let's think about the probability of this Boolean formula in terms of the probabilities of its variables. This one is correct, and it's hard because, I mean, computing the Boolean formula, it's easy, but computing the probability of a Boolean formula is hard. It's at least as hard as satisfiability, right? So see, so the hard part isn't materializing the formula; it's computing the provenance. And this is actually so I actually want to talk to you about this because when I talk about knowledge compilation and circuit classes, by this I mean representing the Boolean provenance in a circuit formalism and restricting the circuit formalism so that probability computation is actually tractable. So it is indeed very related, and I will talk to you about this hopefully. Time permitting. Good. Okay. So let's see what are these probabilistic databases for real, and then let's show results about them. So, and it's been 2 days of tutorials, so I hope now the relational model is something that you're pretty much familiar with. It looks like this, okay? And if I want to formalize things a little bit, so I have a schema where I have relation names that are mapped to an arity, as usual. In the examples, I will often have attribute names to make things more readable, but in reality, I don't care, and I will just use the numerical positions. And then what I call a database instance, a relational instance over a schema, is something that for every relation gives me a set of k tuples, where k is the arity of the relation. And these tuples, you can either write them as rows in the table like this, or as ground facts like this, if you want to think about them logically. So I will use both. I hope you can see that these two are the same thing. And so when we have data and you think about database theory, usually you want to query the data. That's usually what happens. So a query is something that takes database instances over some schema. And I'm only going to focus in this talk on Boolean queries, so queries returning true or false only. So here you can see I'm a theoretician because in practice, queries tend to be able to return results. And why is it that I'm able to get away with this is because I'm only, well, we're mostly going to be concerned about the difference between p-time tractable and sharp-p complete. And since queries, if I fix a query, I have polynomially many possible answers, I can just test every possible answer and get a Boolean query. And so I can reduce to the problem of Boolean querying, just adding a polynomial factor. So in practice, of course, no reasonable database engine is doing this, right? Don't say, let me test all of the only polynomially possible answer, so let's just ground the query. But for what I'm going to do, this is possible, and it will simplify things a lot, not to think about the output of the answers of queries. So which query languages am I going to allow? Conjunctive queries. So I hope none of this doesn't surprise you. So it's an existentially quantified conjunction of atoms. I have atoms, I conjoin them. So you can think about this. So if you see the data as a graph or hypergraph, this is saying I have some pattern in my data. Well, formally, the pattern has a homomorphism to the data. This is an example of a conjunctive query. This is a not especially interesting example of a conjunctive query because you see that this one would be equivalent to removing one of the keeping only the first atom or only the second atom because it has a self-homomorphism. Anyways, I mean, I hope you see what the conjunctive query is. A union of conjunctive queries, it's, well, a union of conjunctive queries. I have several possible conjunctive queries and I take the union. So I'm saying the data has this pattern or that pattern, or I have a finite disjunction of these. And then maybe we will have the chance of seeing first order logic and even monadic second order logic, but I'll define these if and when I get there. Okay. So the data, the queries, and now let's talk about probabilistic databases. So tuple-independent databases, they're the simplest possible formalism, I think, to reason about probabilities over data. And it's extremely simplistic, and I will tell you that it's very limited, and you will see it say, oh, this is not useful because it's too simple. And then we will see complexity results showing that even in that model, many things are intractable, which kind of justifies why people haven't tried that much to go to more complicated things. But I will also present to you more complicated models. So the idea is what's written here. You have an instance. It's a set of facts. You just give a probability to every fact, and that's it. So this is a relational table. You add probabilities. So these are the tutorials from the 3 last tutorials, and here I have improvised the probability that the tutorials would actually happen, you know, like COVID and such. So these are probability pretty pessimistic estimates, but just an example, right? And we assume independence between facts. So thinking about the COVID example, like independence across these is probably not that true. Like if we had to cancel one, maybe we have to cancel the next ones or whatever. So, but this is the simplest possible model. We assume independence. So sometimes people get away with this, saying things like, oh, it's not really independent, but the first order approximation would be to imagine everything's independent. And basically, this is already complicated. And also, if you think about evaluating queries on top of this model, you can introduce correlations through the queries. So also in that way, you can say, well, it's already interesting to think about that. So I mean, this is already enough to keep us busy. So what is the semantics? So I remember this thing about representation systems and such. So this is the probabilistic database. It stands for a set of possible worlds, and the semantics is each fact is kept or discarded with the probability that's indicated. These choices are all independent. So thinking again about this TID instance here, I can think of a possible world which would be I keep the first tuple, I do not keep the second tuple, I keep the third tuple. What is the probability of this possible world, of this outcome of the probabilistic draws? Well, it's simply I had probability 90% of keeping the first tuple. I had probability 1 minus 80% to keep the second tuple. And this is actually a product because these two probabilistic events are independent. So the probability of the conjunction is the product of the probabilities, and times 70% for keeping the third tuple. Okay, and so all possible subsets are possible worlds with the probability defined in this fashion. So, yeah. So again, it's a probability distribution over non-probabilistic databases. The outcome of the probabilistic draws, they no longer have any probabilities in the data, but they have a probability of occurring. So if I have facts with probability 0, I never keep them. If I have facts with probability 1, I always keep them. And so if you try to write formally what I just did in the previous slide, if you have a TID and you take a subset of its facts, the probability is the product of the probabilities of the facts that I have kept in this subset times 1 minus the probability of the facts that I have not kept. And so that's a probability distribution. Or is it? And the probability distributions, there's one important thing that they should do is summing up to 1. And I mean, here it's not completely clear that, I mean, hopefully this is reasonable. And to reassure the more formally oriented people among you, I have a slide to justify that this is actually a probability distribution. So do all of these probabilities really sum up to 1? So if I have n facts, there are 2 to the n possible worlds. So a small quibble, right? If I have facts with probability 0 or 1, some of these possible worlds have probability 0, like the ones where I keep the facts with probability 0 or discard the ones with probability 1. That's still useful to think about 2 to the n possible worlds. And for every possible world, so if you think of the facts of the database, its probability is a product involving factors of the form PR Fi or 1 minus PR Fi. And so now the pretty thing is that if you think about this expression, probability of the first fact plus 1 minus probability of the first fact times and so on for all facts. If you expand this big product, you get 2 to the n terms that precisely correspond to the probabilities of the possible worlds. So this expression is the sum of the probabilities of all of the possible worlds. And you can see that this is 1, and this is 1 times 1 times 1 n times, so it's actually 1. So indeed, the sum of the probabilities of all the possible worlds are equal to this, are equal to 1. So when this is sensible mathematically. Okay. If you didn't understand this, you can just trust me. Okay. And TIDs, can we represent all probabilistic instances with TIDs? So by probabilistic instances, I meant probability distributions over a set of possible worlds. So what do you think? I mean, maybe we can have a vote. Who thinks that we can represent all probability instances with TID? I don't, so who thinks we cannot? Yeah, I mean, we're assuming independence, so here's a concrete example. The class is taught by Jane or Joe, but not by both. So if I want this probability distribution over outcome, so with probability 80% it's Jane, 10% it's Joe, and 10% it's no one, how am I going to represent this as a TID instance? Well, I will have to have Jane and Joe and no one else. Jane will have to have probability 80%. Oops. Okay, the example is wrong. I guess I messed up Jane and Joe, so please substitute one for the other. But in any case, it's going to be that. And then there is an outcome where I have both, and which is not supposed to happen. So this is a very restricted formalism that cannot represent all possible probability distributions. So for the next, I don't know how much time it will take me, but I will present to you two other probabilistic models, BIDs and PC tables, to justify that we can try to handle non-independent things. And then I will not say anything more about these models. So in case you get bored about this, you can go for a nap and then wake up when I stop talking about them. And so if you're confused about them, it doesn't really matter. This is just to give a kind of overview, and also because I think this is simple. I'm more worried about losing in the proofs that will follow than in the definition of models. So let's define models because that's easy. Yes. I don't have, I'm not assuming functional dependencies. Okay, no, BIDs are going to have something to do with functional dependencies, or more precisely with keys. But as a general thing, I'm not making any constraint. I'm not assuming any constraints like FDs or inclusion dependencies on the data. You could think about stuff like if I have an FD, so I have an FD, I have a probabilistic database. What's the probability that the FD is satisfied? Or can I modify the probabilities to incorporate the FD into the data, things like that? I guess you could. I'm not going to do it. So for now, the data is just data without any constraints, and there won't be any constraints in the talk. But they could. Yeah? Okay, so if you're patient, then I guess maybe Jeff also will talk about repairing data to satisfy constraints. So but you will get more satisfactory answers from the next speakers, let's say. Yes. Yes. Yeah, they're correlated. Yeah, sorry, here the Jane and Joe are correlated because they can be true at the same time. Like when you have a probabilistic database that gives some data that are independent, put them like in a block, and you put probability into this block, and just in this way to use dependency, or it's. Wow. This is a perfect question because the B here stands for block, and so you have, I think, invented what I'm about to present. Yes. A probabilistic distribution on what? I guess you could do that. So indeed, another way would be to represent your result as the output of a query run over a TID, and I think this is also possible. Since I'm working with Boolean queries, I cannot do this in my Boolean world, but you could indeed do that if you want to introduce correlations on TID, which is independent. Okay, good. Other questions? So let me answer the question of Liat by presenting exactly what you were thinking of, I think. Block-independent disjoint instances. So this is a formalism that strictly extends TID. So we will, on relations, distinguish some attributes and call them the key, and I will underline the key attributes. So this is a bit like a key as a special kind of functional dependency. And this is what we get. So the line here is for readability. The data is just what's in there. But so I have distinguished day and time as the key, and teacher is not the key. And the idea is that for each of the possible values of the key, I have a block of the corresponding tuples, and I will keep only one block, one tuple per block, or possibly none. So I extend, I put probabilities on tuples as before, but the semantics is no longer the same. The semantics is that for every block, the probabilities should sum up to at most one, and I'm going to choose for every block one fact of the block according to the indicated probabilities, or maybe none at all if the probabilities sum up to strictly less than one. So you can think of this as having a key dependency on these attributes, because in the possible worlds, I'm keeping only one, at most one tuple per block. So this is a bit also like repairing the data to satisfy a key dependency. Or maybe this is related to what Jeff will talk about, maybe not. So yeah, semantics for every block, pick one fact according to probabilities. If the probabilities sum up to strictly less than one, maybe you don't pick any facts. And you do these choices independently across the blocks. So within each block, the tuples are correlated in the sense that they cannot be both true that occur at the same time. And across blocks, it's independent. Okay. So this would be one possible outcome, and the probability of this would be, well, I haven't written it down, but it would be 80% times 1 minus 71%. So, I mean, if you think about applications, so yeah, I'm just seeing this now as abstract objects. The application was that you could imagine that for if Paolo cannot give the talk on Saturday, maybe Floris will replace him. And conversely, but I think we heard that Paolo was supposed to leave early, so I think it's very unlikely that he would stay just to give a talk in the afternoon. So, well. So is BID an extension of TID? Every tuple-independent database can be expressed as a block-independent database. Do you see how you could do that? Yes. Yes, exactly. Every column is every attribute is a key. So every block contains a single fact, and the probability here is the probability of keeping that fact. So this is just a TID. But of course, yeah, can we represent all probabilistic instances with BID now? You could vote again who thinks it's possible, knowing that I'm going to introduce another formalism just afterwards. Okay, so if you think about, for instance, the class is taught by exactly 2 people among Diego, Paolo, Flores. So these are the outcomes that I would like to get. Am I going to be able to have this as the semantics of a BID? Well, if teacher is a key, then I have a TID and I can have only one. So all the tuples are independent. So this is not possible. And if teacher is not a key, then I have one block containing everything. And so I'm keeping only one fact. And so I cannot get that either. So BID cannot express everything. So for the third model to rule them all, probabilistic C tables. Yes? Yeah. No, if I have only one block, it means I'm only keeping one tuple out of the block. Yeah, it's one big block and I'm keeping one tuple of the big block. So I guess there could be cases where you want to do that, but it's not the same thing as a TID. PC tables. So now I'm building more and more complicated models, and you have to think at some point I'm going to want to answer queries over the models, and well, the more expressive the model, the harder it's going to be to answer queries, and we will see even at the TID level, it's already pretty complicated. But for now, we're not trying to do anything with the models except defining them. So let's go wild and define expressive stuff. So Boolean, okay, let's start. So PC tables means probabilistic C tables. So I need to tell you first what a C table is. A Boolean C table, and this is something with no probabilities. We just have a bunch of Boolean variables, and we have on every database fact a condition expressed as a Boolean function, so written using the variables and Boolean operators. You could think of this as provenance if you want, or like, well, a table with some provenance annotations attached, but like if this had been computed for something else, but I don't really need provenance to define this. I'm just saying we have a table or several tables, and for every row we write a Boolean formula as a function of some variables. So this would be an example where you have classes, and for every day the class can be given either by Jane or by Joe, and for a given day there are 2 possible rooms, and I'm writing conditions such that x1 means Jane is sick, and if x1 is true, then Joe is giving the classes. If x1 is false, it would be Jane. And then for the day, for the 11th, I would like to use amphitheater B. So if it's available, x2 is true, we will go there, and otherwise we'll go to amphitheater C. So you can see that here in all possible worlds, I will keep one of the 2 here and one of these 4, depending on the values of these probabilistic variables. The specifics of the example are really not important, but this is just a way to illustrate. And if we wanted to add probabilities to these, well, you can see me coming. I'm just going to put probabilities on the variables. So a Boolean PC table is a database where you have these Boolean annotations plus a probability that of each variable to be true, assuming independence across the variables. Again, this is the variables are independent. It does not mean that the tuples are independent, because I can reuse the same variable in several different places. So the tuples, they're very much dependent. So if you want to formalize it, yes?
So do you now not consider possible worlds as group assignments over the variables?
Not really. So these are all called valuations. And each valuation gives me a possible world. For me, is always a database. So every possible world, every valuation gives me a possible world, which is obtained by keeping the tuples where the annotation evaluates to true under the valuation. Okay. With the one subtlety is that I could be getting the same possible world with several different valuations. The function from valuations to possible worlds is not injective. And so the probability of a possible world is going to be the sum of the probabilities of all of the valuations that give me it. And the probability of evaluation is given by the product distribution on this. Okay, so now you understand. I'm going to make everyone else hopefully understand. So evaluation tells me for the variables whether they're true or false. Each valuation defines a possible world. And for this, if I have a valuation, I consider the evaluation of the Boolean formulas in my table. It's either true or false, and I keep the tuples where it's true and I discard the ones where it's false, and this gives me a possible world. And the probability of evaluation is its probability assuming independence. So the product of the probabilities of variables that are true times 1 minus the probability of the variables that are false. This might sound a bit familiar. It's exactly like if I had a TID for the choice of valuation, but then I do the Boolean evaluation, and so this complicates things, right? And then if I think about one possible subset of the facts, one possible world, its probability is the total probability of all the valuations that give me this possible world. So this is a bit complicated to formalize, but I think the intuition is pretty simple. So here, if we say the probability that Jane is sick is 10% and the probability that anti-theater B is available is 20%, I could think of, so this would be the PC table, a C table plus the probabilities written here. So if I take a valuation, for instance, Jane is not sick and anti-theater B is available, this has probability 90% times 20%, I think, yes, so 18%. And this gives me a possible world obtained by evaluating the conditions. So you see this is false, this is true, and these are false. So I keep these facts. So we go, we have Jane giving the classes, and on the 11th we go to anti-theater B. And the probability of this possible world is the sum of all the valuations giving me this possible world. And in this example, I contain every possible world with only one valuation. Yes? No, it's an arbitrary Boolean formula. So here it's only conjunctions, but it could be anything, really. And there's a question of how you would represent it. So the natural way would be to write the Boolean function, as a Boolean formula. You could also imagine writing it as a circuit, and I'll be talking more about them. So any formalism that expresses a Boolean function is fair game for that stuff. But usually people write these as formulas, and they use the operators that they want. So in this example, every possible world can be obtained by exactly one valuation, but this would not be true in general. Like if I had a variable x3 that was not used, I would have several different valuations giving me the same possible worlds. Anyways, so how expressive is this complicated model? They capture, PC tables capture TIDs because if you just have one, well, each fact gets its own variable with the indicated probability value, then everything's independent and you have a TID. They capture BIDs, so that's a bit more difficult to see. And back in the days where I was teaching this to students, I had this as an exercise to keep them busy and have something that I could test them on at the end. You can engineer Boolean functions with variables that give you a kind of decision tree to select exactly one outcome out of a block. And then getting the right probabilities is a bit tedious, but you can also do it. And then you can express a BID as a PC table. So you can capture BIDs with PC tables. And in fact, so I didn't even make you vote, PC tables can express arbitrary probabilistic distributions. Basically, because if you have a bunch of possible worlds and probabilities, you can write variables that select the possible worlds where you want to get to with the right probabilities, and get again on the tuples, you write a complicated Boolean function that tells you the tuple should be here in precisely the right worlds. You can do this as a DNF. Yes? Not in the model. No, you can use as many variables as you want. Of course, in terms of I'm talking about expressiveness in the sense I can write it. not in terms of how concise it would be to write it or can it translate efficiently. So this translation is obviously a linear time. This translation is obviously polynomial time. You'd have to think a bit more about what the exact complexity would be. And here, and if you write the probability distribution explicitly, I guess it wouldn't be so bad, because since you've already written down all of the outcomes, it's not going to get much larger than this. But if you had a probability distribution that has a large number, an exponential number of possible worlds written in some concise fashion that you wanted to translate to PC tables, but I'm not telling you which complexity you would have. Yes. Yeah, sorry. Yeah, finite support. Yes, sorry. I talked about continuous to say this is scary and I don't want to do this. I know people have been doing this recently. Some of them are even in the room, but I'm not one of them. So everything is finite until I say otherwise. Yes. So why would you restrict the number of variables? You just want to impose this as a restriction? I guess if you had, and I hope I'm not saying nonsense here, but I guess if you have n tuples, you can have 2 to the n possible worlds. But if you have a polynomial number of variables, you're going to get still exponentially many outcomes. So I would imagine that you would only need a polynomial number of variables. Well, okay, I'm afraid of saying wrong things now, but I would think that you would not need more than polynomial variables in terms of the number of facts, but then you could have complicated expressions in terms of these variables, not necessarily polynomial if you want to write down a list of a disjunction of possible valuations of these variables. And so I'm not 100% sure, so it probably is better that we think about it without. Yeah, because I know I'm being filmed. I don't want to have a recorded trace of me saying complete nonsense about these things. Other questions? Yes?
My question is more about the data model. So I know it's natural to think about it as tables, as relations.
Yeah.
Why do you see it as a graph, like what people do in probabilistic graphical models? Like you can express the whole distribution by using conditional probabilities. So when do you come up with this?
So good question. So in terms of, so I know the probabilistic graphical models exist. I don't know that much about them, but I think I can say this. So if you just wanted to represent the data as a graph, you could, and I will do this. I mean, I'm going to assume arity 2 in some of the following slides, and then I will represent everything as graphs because it's so much more pleasant. And then you get, well, every fact is an atom that every fact relates to elements. So you have a colored oriented graph with self loops and probability values on edges telling you the probability that this edge exists. And this is very nice, and we're going to do this. But so probabilistic graphical models, I think, can define more complicated things with factors. And so if you have a probabilistic graphical model where you have hyper edges, I guess, and it's not exactly the same thing here, right? So TIDs, and you have a kind of independence assumption in TIDs, but it's a very simple kind of model where you say, well, this hyper edge either exists or does not exist.
Yeah, no, but I mean, you can connect couples according if they are independent or not, or so you can count it.
Yeah. So if you wanted to, yeah, so I don't think this is exactly done, but if you wanted to do something like this, I think you should think about PC tables, and then the connection between tuples would be, do they use the same variables or not? So with that kind of things, you can maybe say something like, I have each factor is going to be a bunch of variables where I select the outcome of the factor, and then I put these on the tuples that are relevant. But then you need to do some kind of analysis of when you have a PC table, the variables can occur in any arbitrary way. Some PC tables could be simpler than others in that the variables could be, you have mostly independent clusters of variables. So I think I have one paper where we basically figured that if you think about tree width, for instance, you can take the tree width of the data and the tree width of a Boolean circuit annotating the tuples, and you can see this as one big model and do things over it. But this is pretty bleeding. I mean, it's not a very recent paper, but I don't think many people have done that.
And this is the simpler model. But the focus is also on different question. Here, in this simple model, you see the kind of question I understand the sort of that is way more detailed.
Thanks, Benny. Other questions? No? Okay. So yes, and yeah, another thing about PC tables. So one interesting case of expressiveness plus tractability. If you have two PC tables, they all represent a probability distribution. And if you wanted to think about the probability distribution of the union, if you wanted to think about the union of these probability distributions as the possible results of taking the union of one possible world and the other possible world with the right probabilities. So this would be a probabilistic distribution that you can represent with the PC table, but you can do this efficiently given the PC table representations of the initial probability distributions. So we say that they form a strong representation system, as in when you have distributions represented as PC tables, and you want to combine them with an operator from relational algebra, you can efficiently do this at the level of PC tables while having the right semantics. I'm not going into more details about this. Talk to me at the coffee break or what if you think it's interesting. So now everyone that was bored or confused about the description of BIDs and PC tables can wake up. I'm not going to talk about them ever again. I'm only going to talk about TIDs because they're already troublesome enough, even as simple as they might seem. So from now on, only TIDs. And then let's see what I call probabilistic reevaluation. So the terminology probabilistic reevaluation, so PQE, is not ideal, let's say, because it's not the query that's probabilistic, right? It's query evaluation over probabilistic data, maybe a QE, a PD, and so. So what you have to understand is we have a probabilistic database, which is a TID, and we have a query. And the queries are standard database queries. The queries do not see the probabilities. Okay, let's forget about the definitions for now. Let me try and steer you in the right direction. You could think about queries that would look at the probabilities and say, well, select all of the tuples with probability less than 20%. This is not what I'm doing at all. I'm thinking about queries that work on databases with no probabilities, like select all of the triangles of the relation R, whatever. They do not see the probabilities. And I'm thinking about evaluating these queries over the possible worlds of the probabilistic databases, so over deterministic relations. The idea is that I'm thinking of my probabilistic database as standing for a distribution over these non-probabilistic relations. And over each of them, I would want to evaluate my query, and I would want to know what's the total probability that the query is true. So this is what I mean by probabilistic query evaluation. So query evaluation of a probabilistic data, figuring out the probability that the query is true. Connecting back to practice, because I'm very happy to run into complicated problems, but why is this relevant? Well, if you have data with some probabilities and you wanted to evaluate a query over it, I think what you would want to know is basically what are the possible results and what are the probability of these results. Some results are going to be very probable. They will almost always be true. Some others will be very improbable. So you would want to have the possible results and their probabilities. I'm doing Boolean query evaluation, so I'm just telling you what's the probability that the query is true. So you have a probabilistic distribution, and you would want to know, well, what's the probability that I have this pattern in my data according to the probability distribution. So I hope this isn't so shocking. Is there a question? Well, expected database, not really. You could talk about the most probable database, because expected, I mean, how would you average databases together, you see? But maybe you could, I don't know, but I don't know if it's ever been done. But so one thing that looks a bit like what you're saying is you could think about what's the most probable database in my distribution. which in the TID case, I guess, would be obtained by doing the most likely choice for every tuple, right? But I think Benny is going to talk about this in more detail, so I won't step here. So for me, what I want to do is I want to think about the total probability that the query is true over my database. So formally, probability that the database satisfies the query is the sum over all possible worlds satisfying the query of the probability of this possible world. So intuitively, it's the probability of, if I think about this as a probabilistic process where I'm drawing a possible world, it's the probability of drawing a possible world that satisfies the query. And so, yeah. The problem is, given it, if you fix a query, the problem PQE of that query is given the TID was the probability that that the query holds. So to give you an example, so this is another TID containing details about secret agents of several kinds in several countries or whatever, and with probabilities because we're not sure of what we've inferred about the secret agents. And we want to know what's the probability to have a tuple with value New York. And so, okay. So those of you who don't want to think, the machines, they would just, one way to always do this would be, let's just write down every possible world with the probability. Let's check which ones have New York and which ones do not. And then let's do the sum. But we can always do that. So this would be 2, 4, 8, 16, 32, 64, 128. You could do it, maybe taking the rest of the morning or a bit more. You could do that. But in fact, so if you're a bit more clever, what can we say? So all of the tuples that don't have New York, we don't care about what the outcome is because they're not going to influence the result of the query. What matters is over these two tuples, whether I get one of them or not. So we're down to four possibilities. But if you think a bit more, basically, I'm just doing the or. So I'm saying I want this one or this one. So the probability of keeping one of the two is 1 minus the probability of keeping none of the two. And probability of keeping none of the two is a conjunction of not keeping that one and not keeping that one. And these two things are independent, so I can do the product. So I can really do it without any enumeration of explicit enumeration of possible worlds. I get this. So the probability of getting a tuple with value New York is 1 minus the probability of not having any tuple with value New York. And this is the product of the two independent events. I do not get this and I do not get that. And not getting this, the probability is 1 minus the probability of getting it. And you get the idea. But this is already a bit complicated and this is going to get worse. Okay, so let me try to rephrase again formally what this problem is. And it's really important that you get it because the rest of the talk I'll only be talking about that problem more or less. So if you're confused about the definition, really, you shouldn't allow me to continue. So formally, we fix a Boolean query, for instance, a conjunctive query. We are given as input a tuple-independent database, a relational database where the facts are independent or annotated with probabilities. And I'm asking, can I compute the total probability of the possible worlds of this TID instance that satisfy the query? I insist that I am studying data complexity. So it's been covered in the previous talks. Data complexity means the query, it is fixed, and the input, it is the database. And so the problem is parameterized in a sense by the query that I'm thinking of. And well, okay, so how can we solve this problem? And I tell you, it's always possible to solve the problem naively by going over all of the possible worlds of the input with their probability, running the query over the possible world and summing the probabilities of all the worlds that satisfy the query. We don't want to do this because this is exponential, right? Hello? Yeah. Okay, well, okay, I have written it down for you, so you can always, you have the TID, you have the query. If you don't want to think about it, you can just write every possible world. It has a probability. Does it satisfy the query? Yes, this one does. These do not. And so the probability of the query is this. If you wanted to implement it, you could do it like this. It's always possible, but it takes exponential time in general. Even if, okay, so this would mean even if there are not many possible worlds satisfying the query, because if you do it naively like this, you will spend lots of time with unproductive possible worlds. If there aren't that many tuples in the input, you can do this, but otherwise it's not reasonable. Let me say that this is an exponential time algorithm. It's a bit like NP versus X time. This isn't the crispest thing I can say about the complexity. This would actually be in the class sharp P. So I'm going to define it, but if you don't get the definition, it doesn't matter. You could, if you think of this as NP, it's almost true, except this isn't a decision problem, right? It's a computation problem. And what I want to compute is a probability, so it's actually a counting problem, except I'm counting a fraction instead of an integer, whatever. So formally, what is sharp P? Sharp P is the class of problems that can be the class of counting problems. So given an input, I produce a number, where this number can be expressed as the number of accepting computations of a non-deterministic Turing machine that runs in P time. So you think about a non-deterministic Turing machine, like I'm going to play the non-deterministic Turing machine, and then the machine runs, and it's not deterministic, so sometimes it gets, and some of these choices the machine will reject, and so they're not counted, and some of them the machine will accept. The total length of the length of a run is bounded polynomially, so the machine cannot go on for too long. And then on the input, I look at how many computation paths have accepted, and this is the number that the machine computes. So NP is, does there exist a path? Sharp P is, how many paths do I have? And this isn't really computing a probability, but up to normalization, it is. Because if you think of a TID, if you just wrote every probability of tuples as a fraction, and you just multiplied by all of the denominators, you would have the normalization factor. Basically, the result is 1 over this product of denominators times something which is an integer and which you could compute exactly like this. So if you wanted to do it really, it wouldn't be so pleasant because, so the basic idea is how to do this problem in sharp P, but the non-deterministic Turing machine guesses non-deterministically a choice of tuples, and then checks the query in deterministic P time and accepts or rejects, and then you just sum over the choice of tuples where the query is satisfied. The problem is that because of the probabilities, you would need to bias a bit the computation. So like if a tuple is more likely than another, you would need to make the machine do lots of guesses that don't matter just to give more weight to that outcome. But this can be done. I mean, you can do something, but the machine is going to weigh the paths according to the tuple probabilities anyways. So this is doable. It's in sharp P. And since probabilistic evaluation is computationally intractable, and we'll see why, it's unlikely that we can beat this naive evaluation in general, but maybe for some queries, we can do it. For the New York query, for instance, I found a way to do it without enumerating all of the possible worlds. So, okay, so we still have a bit more time, good. So I will give you some examples, and then we're going to try and systematize them to come up with a characterization of what are the feasible queries and the infeasible queries. But I hope at this stage, the motivation of this is clear. So I have TIDs, reasonable probabilistic database framework. I have queries like conjunctive queries or things like that. I want to know their probability. I have this baseline naive algorithm, which is X time or sharp P. And in some cases, I can do things more intelligently than counting all possible worlds or doing some non-deterministic stuff for possible worlds. Sometimes we will see we cannot do it, and conditionally to FP different from sharp P or whatever. And we want to know what's the frontier, what are the simple queries and what are the complicated ones. So let's probe a bit at the frontier. And let's take a very complicated query here. If I have this query, how do you compute the probability of this query? Without going over all the possible worlds? I could phrase this as an exercise and ask if someone has a proposed algorithm. Yes? Huh? But what did you say? Yeah, I want to know if there exists an R tuple. So how do we do that? How do I do that? Yeah. So it's an independent OR, right? I want this tuple or this tuple or this tuple, all of these being independent. And so it's well known that in probabilities, independent AND is easy because it's the product of probabilities. Independent OR, I need to do this trickery of going via 1 minus, which is a bit like using De Morgan's law, right? X or Y is not X and not Y. So do we have an R fact? It is 1 minus the probability of not having an R fact. Not having an R fact means that for every R fact, for every R fact, I do not keep it, which is 1 minus probability of keeping it. So that's the answer. And this is something that I can evaluate in polynomial time, right? This product is over linearly many tuples. That's okay. Far more complicated. Well, you see, well, this is a query that doesn't look that bad, but it is already pretty complicated. What's the probability of this query? So this is asking, I have an R fact, and then this R fact has an outgoing S fact. Can you see an algorithm? Yes. Yeah, kinda. So, but maybe the question is, why is this? Why is this true? Why does this work? Mm-hmm. Mm. Yeah. 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 No, but the important thing I'm trying to get you to is that in the join, what's important is that you are partitioning the S tuples depending on the first item. So doing trigger happily joins on TIDs is dangerous because you cannot generally combine the probabilities because of correlations. But here specifically, it works because for every X, you're going to look at the outgoing Ys, and this is a partition of the S facts. So there is no S fact that is involved in two of these X values. So yeah, so the way I see it is basically this. So you could think about for every element of the database, what's the probability that there is an outgoing S fact? And so for every element, you compute this probability as an independent disjunction of having kept what of the outgoing S things. And then you see, well, for every element, I have a probability of having both R and an outgoing S fact. And then I have the probability of having one of these things being true that I compute like this. So if we try to write this down together, you will see it gets pretty unpleasant. So is there an R fact that also has an outgoing S fact? So we're doing this, and what I'm saying, what we're doing is basically doing a case disjunction based on the value of X. We say, well, either X is A, or it's B, or it's C, and depending on this, we are partitioning the facts. So if you try to write it down, it gives you probability of this being true is 1 minus the probability that it's false. Being false means over all possible values for X, it is false, and I do the product. And these are independent because across the values of X, I'm talking about, well, of course, different R facts, but also different S facts, and partitioning the S relation based on the first attribute. And so for every value of X, this is false. So yeah, this being false for a given value of X means 1 minus the probability that it's true for that value of X. And if it's, so for X equal A, if this is true, it means I have the fact R of A, and I have one outgoing S fact, and the probability that I have one outgoing S fact for X equal A is 1 minus the probability that I don't have any, and this is the product over all values B of Y times the probability of not having that that S fact. So yeah, not very pleasant, but this is P time to evaluate. And the point of this example is not that this isn't especially important, it's just to say, see, there are complicated things happening and we need to figure out what is going on and how do we generalize this. Okay? And as I tried to explain to you, the reason why all of this works is because these products here are independent. These are products across different values of X. These are products across different values of Y for a given value of X. And this is a product between R and S. So all of this stuff is independent. Now for a more complicated example, well, an extremely complicated query with 3 atoms. What is the probability of this query? Do you have a p-time algorithm for computing the probability of this query? If you have a p-time algorithm, give it to me and I will figure out something interesting financially to do with it. So this one is sharply hard, right? And so here we see it's already bad news. I'm thinking about probabilistic correlation and such. We took the simplest possible model, TIDs. We take this not very complicated query and we hit sharply or hardness immediately. So, I mean, in the normal database world, when you run queries, you don't expect that this query in data complexity would be intractable to evaluate. When we have probabilities, unfortunately, that's the case. So we get after 1 hour, we get at last to the research question of what I think is an interesting question about these probabilistic databases. Which queries can we efficiently evaluate, like these two, and which ones we cannot evaluate efficiently, like this one? Could there be a dichotomy, like a characterization of the tractable queries? Fortunately, there is. Yes. Yes. Yeah. So once someone told me about probabilistic databases, they told me in practice, why do you care so much about exact evaluation? Because in all of the motivating scenarios, the probabilities are something like, oh, it's some confidence value from a learning algorithm. And so why do we care about getting the probability correct to the last decimal digit instead of doing gross approximations? So I think if you really wanted to do something practical, it means, the model is not the right model. And especially the task of exact probability computation is maybe not the right task. And instead, you could do approximations. I will talk about approximations at the very end of my talk. Even though I think this is a very relevant question, it's a question on which it's hard to say anything intelligent theoretically, which is why I don't have so much to say about it. And basically, you can have additive approximation by Monte Carlo sampling. Then you have a multiplicative approximation by the Carp-2B algorithm, which is nice, but it's known, and then it's not clear what else you can say, right? But other than that, I guess, another thing you could say, is maybe you don't want probabilities after all. Maybe you want some quantitative reasoning of saying, well, I have facts that have these scores. Like, for instance, what Val was saying about I have these costs of facts and I combine them in a summary and I don't care about correlations. And maybe, if you want to do things in practice, this is what you should do. And so, it's true. At that point, we have gotten off track about the practical motivations, and we're running into something which is just, in my opinion, a disguised way to study counting algorithms on homomorphism type problems and a kind of crazy CSP variant of counting subgraphs of something. So, which I personally think is interesting, but I agree that if you're interested in practice, maybe you don't care so much. Yes.
What about the not approximating, but rather having a threshold and checking whether the probability is greater than the threshold?
That's a good question, and I've never thought about this. I don't know. Does someone know?
For this question, yes, but there are other problems where this is
For which question?
At least
for which question do you say it's doable?
I guess for this question.
This specific query?
Yes.
Okay.
But I think there are more than one query where this problem is because then you can just reduce it to checking whether an NP problem has a solution or not. Threshold if the probability is 0 or not.
Yeah, but I mean, if you think about reasonable queries like UCQs, where the provenance is a monotone Boolean function on which it's easy to check satisfiability, I don't know if I don't know. Yeah.
You do like a binary search, but your precision is limited. You can actually get that probability.
Yeah. So if you could compare to it, so you're saying basically it's intractable because if you could do that, you would get to the exact probability by doing binary search. Yeah, true. Okay, so then I guess that's true. So unfortunately,
Also, about the question of queries. To me, such a dichotomy tells you when or what are the types of queries where you have exact algorithms that do not care about the data, and in which cases you need to give approximation. Theoretically, you need to use approximation, and you need to look into the data pre-weight. I think that harness results are practical. They just tell you, don't look for a general algorithm. Look for something more.
Yeah, so you're better at selling this than me. I would say that even, well, because of course you could answer okay, so but then there aren't that many queries where you're going to be able to do it exactly. But probably something you could say is, if you look at this kind of phenomena, you could have a query that's intractable globally, but that has this kind of dangling things where you can simplify these away exactly by rewriting the data and then doing approximations. So this would be guiding you in a sense to tell you what's the part that you have to approximate and what you can compute exactly. So yeah, that's true. That's a more optimistic thing to say. No more questions? Okay, so 20 minutes before the break, so I think I have time to tell you maybe not all of the dichotomy, but at least a good part of it. So the question is, yeah, what are these tractable queries and what are the intractable queries? What's the complexity of probabilistic evaluation depending on the query? Remember that we are studying data complexity. So again, the query is fixed, and I'm asking for which fixed query is the problem tractable, for which one it isn't. And so we've seen for this one, the problem is hard. So what's the frontier? So this dichotomy is due to Dalvi and Suciu in well, several papers, but I distinguish it between what I call the small dichotomy in this paper, so this is about conjunctive queries that are self-join free. I'll explain what this means. And for this talk, I have even simplified it further because I think it's easier by saying the queries are arity2. So in this paper, what they show is the dichotomy for this and this, but this is my extra hypothesis that they don't do. And in the 2012 paper, it's the large dichotomy that works for arbitrary UCQs, so without arity2, of course, but without self-join freeness and going to unions. And this is far, far more complicated. And the results, the dichotomy, so they get dichotomy results. So it means the problem is either tractable or intractable. So it's like 4 queries in a certain class, for a query Q in a certain class. If Q has a certain form, then probabilistic evaluation is in P time. Otherwise, it is sharply hard. So that's first, I mean, I will explain in detail the small dichotomy, and then the rest I will sketch, I will hint at the fact that it exists. So the small dichotomy applies to conjunctive queries, existentially quantified conjunctions of atoms. Under the arity2 assumption, so this is basically to have nice drawings on the slides, and now you see we have probabilistic graphs, so all the relations are actually binary relations, so you can think of it as edges of a certain color in a graph. And I will also draw the queries like graphs like this. And self-join freeness means the conjunctive query doesn't use the same color twice. So I have a conjunctive query, which is a kind of graph pattern, and every edge has its different color. So this, for instance, is an arity2 self-join free conjunctive query. The previous examples, I think, were also arity2. Well, I also had unary facts, so it doesn't matter, and self-join free. And then the result is the following. Ta-da. If my CQ, so for queries that are CQs that are arity2 and that are self-join free, if they are what I call a conjunction of stars, that's my personal terminology, then the problem is in P time. Otherwise, it's sharply hard. What is the conjunction of stars? So think of it visually. So what I call a star is a CQ on an arity2 CQ with a separator variable that occurs in all edges. So it means it has a variable which is a center of the star, and then the star has rays, so going to other variables, but all of the edges involve the variable y. So you can have edges in one direction or the reverse direction, or in both directions, and you can have multiple edges, but all of the facts in the star involve the variable y, which we call a separator variable. And a conjunction of stars is just a conjunction of several disjoint stars. So this is a star, this is a conjunction of stars. And this is not a star because there is no variable here that occurs in all of the facts. And this is the key of why this is intractable, whereas we will see that this is tractable. Okay? You get the definition. I mean, we hope you'll be able to recognize a star and a conjunction of stars now when you see one. And I claim that things like this, they are tractable, and everything else is hard. So let's see why the tractable things are indeed tractable. And I mean, it's basically what I was preparing with the RxSXY example. This is just a generalization of this. So we're going to do it step by step on an example, and then it generalizes. So how do we solve probabilistic reevaluation for Q, a conjunction of stars? So we have like this, several stars. It's self-join free, so every color is unique. what would be the first step? First step is that we're going to process each star separately. And we say the probability that the query is true is the product of the probability that each of the stars is true. Why is this reasonable? Because the stars, they are disconnected, so I can evaluate them separately. And the conjunctions are indeed independent. Because of the self-join free assumption, I don't have the same edge color in two stars. So all of the stars are talking about different relations. So it's basically, I split my database into the right relations. I split my query and I do the product. So from conjunction of stars, it's easy to get to evaluating a star. How do I evaluate a star? I use the presence of a center of a separator variable. And I'm going to do, as before, I'm going to think about all the possible choice of values for these variables and then think about the probability that I have the outgoing things that I should have. So I go over my database and I look at every possible value of the domain and I think about each of these possible stars with a specific element as the center. And I claim that there is a match of this in my database if and only if there is a match of one of these. And the reason for this is that it's pretty obvious, but I mean, if I have a match of this, then I have a choice of the center variable. And if I have a match of this, then I have a match of this. But the important thing is that all of these things here are now independent because the database facts involved in a match of this or of this or of this are disjoint. The specific fact of the database cannot contribute to a match of this and a match of this because you see that the facts are partitioned based on so for the brown facts, it's the first element, for the green facts, it's the second element. So when I take all elements of my database and think about all of these instantiated stars, I can partition the database based on the facts that could be useful for this, the facts that could be useful for that, and so on. This gives me like lots of small queries over lots of small databases, and I can evaluate them separately. Like I have partitioned the facts, so it's an independent OR, an independent disjunction. Yes, right. Yes, it does, because if this was brown and this was brown, you could have the brown thing involved in both the first and the yet. Indeed, important. This subtly uses the self-join free assumption. Yes. Now I have a star and I have a choice of element as its center. So what are we going to do? Well, we think about all of the other variables, and it's as if we had different connected components now. We have this thing here, and this thing here, and this thing here. And thanks to self-join freeness, these are also independent. Okay, so for every match, we consider every other variable, and it's having this in the database is a conjunction of having this brown A to a brown thing, A to a blue thing, and A in this relationship with this variable. And this is an independent conjunction because it's different relations. So I'm focusing on that one because it's the most complicated. And now what do? We think about all the possible values of this X element. And again, thanks to self-join freeness, we are partitioning the database based on, for the value A, we look at all the other possible elements and we partition the facts, saying the ones where it's with the one with A is related to B1, with B2, with B3, and so on. And this thing here being true is an independent disjunction of one of these being true. And now that we have instantiated and we have only one of these, we can think about all the explicit facts written here, and I need to have all of them. And so again, I was about to say thanks to self-join freeness, but now it's obvious because I can't have the same fact twice. I'm just writing now the product of these probabilities, and I just read off, once I have done to a single fact, I just read off its probability in the database. I have the impression that this was a bit mystifying. So if you got the R of X, S of XY example, this is the same thing, just a bit more general and more complicated. But you see, the key insight is that you are basically having two steps. The one where you have different connected components or different branches of a star and you do an independent conjunction. And the one where you instantiate a variable that occurs in all of the atoms and you split the atoms based on that variable, based on the value of that variable. So this justifies that it's p time to evaluate these conjunctions of stars. Do you have questions about this upper bound? Otherwise, I just have time to tell you about the lower bound. And so for the lower bound, this is my prime candidate of an intractable query. It's the query I have told you it's hard, the RST query. And I'm claiming without proof, well, okay, no, not in this case, it's obvious actually. If I have a self-join-free CQ, which is arity2 and which is not a conjunction of stars, it means that it has a pattern like this, where I have three atoms like this, because otherwise it would be like the stars. I mean, I have paths of length 2 basically, and if something is not a conjunction of stars, then in some connected component I have a path of length 3. So I have something like this. Well, okay, maybe I have more. Maybe the edges are in a different direction. Maybe I have several facts or whatever. But for simplicity, I focus on this specific pattern, and we're going to show that probabilistic query evaluation for this query is intractable. And like if there are other facts in my query, like other conjunctions of stars, other branches or whatever, these are on separate relations. I just put in my database all possible facts of this relation, like the quadratically many possible facts of this relation with probability 1, so that I know that they're here. So I might as well remove them from the query. And so I can basically reduce from the computation of the probability of this query. And so this is the important case to look at. And we'll see that this is sharp P hard. Yes. X and Y are equal. So, okay. It could be the case that the red edge is actually a unary query. It could be the case that the blue edge is actually a unary relation. So yeah, here I'm basically glossing over the fact that in arity2 you can still have self-loops. So yeah, this could be true. Or it could be the case that it's like this, but X and W are equal. That would also be possible. It doesn't make a difference, but you're completely right. I'm sweeping things under the rug here. Okay, so why is this hard? So we're going to do a reduction. Like usually when you show hardness of something, in computer science, we don't know to show that things are really difficult. We just know how to show that things are as hard as something else that we don't know the complexity of. So what we don't know the complexity of is satisfy the SAT problem on Boolean formulas. And here for the counting version, it's counting the satisfying assignments of Boolean formula. Okay, so if I have a Boolean formula, SAT asks me, do I have a satisfying assignment? And sharp SAT is count how many satisfying assignments I have. So SAT is NP hard, sharp SAT is unsurprisingly sharp P hard. But what's more surprising, and to me, when going into this was a surprise, is that when counting things can be much harder than checking the existence of things. And so sharp SAT is hard, even in cases where the corresponding satisfiability problem is easy. Sharp SAT is already hard for very restricted formulas on which Boolean satisfiability is trivial. And these are the PP2 DNF formulas. So let me present to you this weird class of formulas. These are Boolean formulas that are partitioned, meaning the variables, there are X variables and Y variables. Okay. Positive, no negation. So here you already see like satisfiability of positive formulas. Pretty easy, right? But counting how many satisfying assignments I have is still hard, even though the Boolean satisfiability problem is easy. And the formula is a 2DNF. So I mean, you might remember, oh yeah, 3SAT is NP hard, but 2SAT is P time because there's this complicated algorithm. So here I have a 2SAT for DNFs that are positive, and where additionally each clause is a conjunction of X and one X variable and one Y variable. So that's why it's partitioned. Yes? Yeah, it's approximable. I mean, it's sharp SAT, you can always approximate it additively. And if it's in DNF, you can always do carp2b and get a multiplicative approximation. So yeah, when I say it's hard, I'm always thinking about exact computation. If you're okay with approximations, as I've argued in practice, you should probably be. Well, this isn't so scary after all. Yeah? But exact computation, intractable. So this is an example of such a formula. So you see what it looks like. It's just a disjunction of conjunctions of two positive variables, one X and one Y. And I'm telling you, this is from an old paper by Proven and Ball, that this counting problem of counting the satisfying assignments of these things is sharp P hard. It has also a graph interpretation that I'll tell you about. But so let's reduce from counting the satisfying assignments of this formula to counting to probabilistic reevaluation for this query. And for this, let me, from the formula, build a database, an instance. I'm going to do it like this. I'm going to have red edges on the left with probability 1/2 corresponding to the x variables, so x1, x2, x3. Blue edges on the right corresponding to the y variables, y1 and y2. So these are the variables, and so the clauses, now what am I going to do? Well, a clause between an x variable and a y variable, I code it as a green edge with probability 1. Okay? So now I have 1, 2, 3, 4, 5 edges corresponding to my 5 clauses. And you can see, I mean, one other way to think about satisfying this is selecting some x variables and y variables such that one of these clauses has 2 true variables. So they are like, there is one edge of the graph where the left element and the right element is true. So it's a bit like the negation of counting independent sets. But I won't tell you more, but I mean, and you can also, let's see why this is connected to probabilistic reevaluation. The valuations of phi, the choices of making the x and y variables true or false, correspond to possible worlds of I phi, right? If I select x1 to be true or false, it's like selecting this edge to be present or absent. There's a bijection between the x variables and the red edges, the y variables and the blue edges. And it's probability preserving because all possible worlds of this database have the same probability, like 1/2 to the power of the number of variables. And I claim that evaluation satisfies this if and only if I have made 2 variables, x and y, true that are in the same clause, if and only if I have in the corresponding possible world a kept red edge connected by a green edge to a kept blue edge, which means a match of this query. It means that counting the satisfying assignments of this is exactly like counting the possible worlds of this that have this pattern up to normalizing by 1/2 to the power of the number of variables. And so, yeah. So then this shows sharply hardness, right? Counting this clearly reduces to computing the probability of this, even on very restricted instances of this form. And you see an interesting phenomenon here is that I have only used probabilities 1/2 and 1. And so I don't need other probability values. And you could ask, do I really need the probability 1 here? Or could I only do it with probabilities 1/2 everywhere? Because this would be like counting subsets without any weighting of the subset. And the answer is yes, it's also hard in that case. But this I will talk about at the very end. We did this with Benny a few years ago. Maybe, I mean, okay, so it's almost time for the break. Let me maybe finish with the dichotomy because now we're done with the technical material. I'm just going to wave hands to tell you what happens in the more complicated cases. So this is the dichotomy for self-join-free conjunctive queries in RET2. If it's a conjunction of stars, it's easy. Otherwise, it's hard for that reason. And so let's lift the hypothesis and see where we get to. So RET2, removing the RET2 hypothesis, it's still reasonably easy to understand. And this is what was done in Dalvi and Suciu 2007 paper. So let Q be a self-join-free CQ without the RET2 restriction. And the tractability criterion is no longer being a conjunction of stars, but a generalization of this, which is being a hierarchical query. And what hierarchical means is a query that's built by conjunctions of separate connected components, like the conjunction of stars thing. And otherwise, if you're connected, having a separator variable that occurs in all atoms, and when removing this variable, recursing into queries that are themselves hierarchical. So that's like the higher RET generalization. So if you really understand the process about the stars and stuff, you can see that this was you could do this inductively. So I've only did 2 steps of it by saying I have separate stars, and then within a star I have separate branches. If you generalize this to a higher RET, you get precisely that. So to give a graphical representation of these queries, so it's not that pleasant to represent, but I like painfully drawn one here. This is a query where you have like different connected components. I mean, so this is the query, and this is a representation of the hyperedges of the query. You have different connected components, and within each connected component, there is a root variable that occurs in all of the atoms. And when you remove, if you hide the root variable and you recurse in the rest, basically you remove X from all of the atoms, you get connected components that are themselves hierarchical in this sense. So you would have here 2 green things, with this one being the root variable. Here you would have just 1 atom. Here you would have this thing with the purple and the orange that is again hierarchical. So it's okay, and just trying to give you an insight of what's going on. And then these things are tractable for the same reason as before. So the proof is the same, and we're still doing the same steps of doing independent OR of connected things on different relations, and independent OR when we have a component taking its root variable and saying it's either that value or that value or that value, and arguing it partitions using self-joint freeness in all cases. And for the lower bound, it's the same thing. So even in higher RET, a non-hierarchical expression contains a pattern like this, except, well, it can be multiple variables, but you can basically get to this by removing atoms that you don't care about and removing variables that you don't care about. There's the key to this is an equivalent characterization that if a query is not hierarchical in the sense of the previous slide, then it must have two variables, and so like this, and an atom that contains both variables, an atom that contains one variable but not the other one, and an atom that contains that variable but not the other variable. Basically, if you don't have this root variable, it means that at some point you have these 2 incomparable variables, and then you can use these 3 atoms that look a bit like this to do the reduction. Okay. So this is the case of self-joint free CQs without the RET2 restriction, and it's the same idea, just in higher RET. And if you want to go without the self-joint free assumption and going from CQs to UCQs, the dichotomy is this one. So if the query is handled by a complicated algorithm, then probabilistic query evaluation is in P time. And in all cases where the algorithm fails, it's sharply hard. So this is a completely baffling, to me, result. I mean, it's not like there's a characterization of the tractable queries, really. It's just like there is an algorithm that does things that are indeed p-time and correct. And if it cannot do them, then it says, I'm stuck, and it gives up. And then there is a very complicated hardness proof to say, well, in the minimal cases where the algorithm got stuck, then indeed you could do a reduction to show hardness. But it is, I mean, it's a very, very challenging result. What I think is interesting is that, so in the algorithm, well, there are unpleasant details like something called a ranking transform that show up. And even so, once you've done this, the algorithm is basically doing independent ANDs and independent ORs like before. So it's a bit similar, right? Because it's doing independent conjunctions on symbol components, independent conjunctions on connected components, and ORs on separator variables, with a refinement to account for the possible existence of self-joins. So but it's also doing something very mysterious. It's using the inclusion-exclusion formula. So it's doing things like X and Y is probability, X or Y is probability of X plus probability of Y minus probability of X and Y. And so this can reduce from between conjunctions and disjunctions like in a very informal sense. And this is important for the algorithm to work. And it's even important for the algorithm to do this. And notice that in some cases, there are some terms that cancel out. So like in the inclusion-exclusion formula, you get logically equivalent terms that cancel out. And like these terms can be intractable to compute, but because they cancel out, the overall formula is tractable. Very, very mysterious. Okay, and the lower bound is, I told you, saying when the algorithm gets stuck, then it is in fact intractable. So that's the general result, and it gives us a characterization, albeit not a very pleasant one, of the unions of conjunctive queries where this probabilistic query evaluation problem is tractable, and the other ones where it's intractable. So I think that's a good moment to take a break, unless you have questions about this. Yes?
For the tractable queries,
it's open. They say in the paper, we don't know what the complexity of the algorithm in the query is. Well, I hope I'm not saying nonsense, but I think here it's tracted. I'm decomposing a query in hierarchical components like this, or saying it doesn't work, I think it's definitely p time, and well, is it linear time? I guess. Yeah. Yeah. But I think what. But I think this is. So the reason why I was answering that way is that I think once you have the decomposition of the query as root variables and so on, I think it's tractable, right, in the query also, because sorry, these are actually acyclic queries, I think, and because doing the conjunction over the connected components is tractable. Instantiating all of this is also tractable, and then in the end you just check if specific facts exist in the database. So it is tractable also in the queries, and the reason for this is that you're basically imposing a kind of a cyclicity on the queries, I think. So for the self-join free CQ case, I think it's also tractable in the query for that reason. For the RET2, in the RET2 setting, in the non-RET2 setting, I think computing the decomposition in connected components, root variables, and so on is not complicated, because it's just like doing connected components, and then within a connected component, count how many times a variable occurs and check that there's a variable that's in everywhere, and then take it, remove it, and recurse. And but for the UCQ case, the meta dichotomy question of figuring out if the algorithm is going to get stuck or not, it's left open in the paper explicitly. They don't know what the complexity of the algorithm is in the query. It's elementary, I think, at least. I don't know if it's worse than next time, and I think it's open whether it can be done in p time. And I think the bottom line is that we don't understand personally, I don't understand the algorithm well enough to answer this, but apparently Dalvi and Suciu don't also. So, so yeah, I mean, this is. I'm thinking about the strategic view of research. This is a solved problem. This problem has been solved for 10 years. It's solved in the sense that there's a paper that proves it, but it's not solved in the sense that we understand it well enough to answer these kinds of questions. So there is an open problem of understanding this.
In the case of RET2, there's something intelligible, like this algorithm.
That's a great question. So I had a hope, like recently I figured, oh yeah, I'm going to understand this in the specific case of RET2. And then it turns out that the hardness proof like is in 3 steps. And the first 2 steps are basically going back to RET2, and they are not the most complicated steps. And then the 3rd section begins by, now we are in RET2 in a setting where we are bipartite. So again, the domain of the instance is partitioned into 2 things, and then we only have RET2 things going from one to the other. And then we're going to show hardness of that, and then it goes on for 20 or 30 pages with complicated maths. And so this case is it's the important. So I think they set themselves as the most interesting part of the proof. So I think it's the proof is getting to the RET2 case, and then this is where the interesting things happen. So we've seen which queries are hard, which queries are tractable. And in the second part of the tutorial, I want to present to you 2 main things. I want to talk to you about, for the tractable queries, can we understand the tractability in a better way than just saying we have an algorithm that computes something numerically? Like, can we symbolically understand what's going on, and can we connect to circuit classes? Unfortunately, I won't be able to give you a new result out of this. It's just going to be, well, the tractable queries are still tractable, and here's a different explanation, or like a different way of seeing what the algorithm does. But then this is going to unlock something for the second part, where like the second part, I want to talk to you about width restrictions of the database and connections to true width and such. And there, like the connection to circuits is very important, and I think is the right way to understand tractability. And then we'll see like what time's left to talk about recent results and so on. This we talked about. Yeah. So connections to provenance circuits, what Val presented to you, and knowledge compilation. So let's remember some things from yesterday morning. If you have a relational database and you have a Boolean query, you can talk about Boolean provenance. So if this is a query and this is a database, the provenance would be what I call the Boolean provenance is a Boolean function that tells me if every fact has its own variable. It tells me when the query is true and when the query is false. So it's a Boolean function, which I will represent as a Boolean circuit over the facts of I. So I'm assuming each fact has its own variable, which I just write as the fact. And the Boolean formula should evaluate to true precisely when the fact precisely on the valuations corresponding to subsets of facts that satisfy the query. So here, like this would be the provenance, the Boolean function, the circuit representation of Boolean function. So let's go through it. The query is saying I have an R fact and then I have an S fact that share the Y variable. So basically I need to have the one S fact that's here, and I need to have either one of these two facts with this junction like this. So this is a Boolean function which I choose to write as a Boolean circuit. I hope that's okay. I mean, it's related to what we saw yesterday. Yesterday, Val told you about semi-ring provenance and computing a semi-ring expression. What's the difference? So I only care about Boolean provenance. So all of the things like multiplicity of facts, multiplicity of derivations, I don't care. I mean, I just need to know on the subset of facts, is the query true or is it false, not how many things and so. And the other reason is that defining provenance in terms of the multiplicity of derivations or multiple uses of the facts is something that's more operational about evaluating the query. I only see the query as a black box that takes a sub-instance and says yes or no. So I only care about this Boolean behavior. And I'm using circuit representations, which are more concise than formula representations. So this sounds a bit silly, right? It sounds like, now, I mean, from my perspective, it seems if you want to write a Boolean Boolean function, why not use a circuit? It's more, it's at least as concise, and sometimes it's strictly more concise. But surprising as it may seem, using circuit representations of Boolean functions in this setting for provenance is something that's relatively new. I mean, that wasn't what the people did at the beginning. Okay, so what I'm going to call the intentional approach to probabilistic reevaluation. So, well, the extensional approach would be we run an ad hoc algorithm to compute the probability, or like people use this usually to mean I have a relational query plan and I evaluate the query and I compute probabilities along with the query evaluation. Intentional means I compute a representation of the Boolean provenance, and then I compute the probability of this Boolean provenance by arguing that it falls into a specific tractable class. Okay, so it's a more modular thing, 2 steps. First, you compute the Boolean provenance in any way you like. And then you argue that then you argue that the way you used to compute it, or that you can rewrite the provenance to be in a tractable class where computing the probability is tractable. So why do it like this? It's more modular, just in terms of writing down a proof, it's more modular. It means that numerical computations don't need to happen within the proof. I don't like seeing a proof that says we multiply these probabilities and they are independent, so that's okay. And then you basically entangle the numerical computations with the justifications of why they're correct and such. Here you are computing the Boolean lineage, and then you're forgetting completely about the query and about the answers. You just have a Boolean function. And the invariant, like basically the interface of the 2 boxes, is the restricted class of Boolean function representations, so the Boolean circuit class that you're using. And it has the advantage that these restrictions are not completely ad hoc because they were already used before in the field of knowledge compilation. So knowledge compilation, I will only give a very hazy definition. This is a field of people that look at representing things as Boolean functions in specific circuit settings that make things tractable, and they look in particular at which kind of tractability restrictions can you impose, what are they good for, can you translate from a circuit in one class to a circuit in another class, what's the complexity of doing that, can you separate the classes? And a justification for this modular approach, so in this talk I'm only talking about probability evaluation, But there are other things in life that you can want to do, like enumeration, for instance, or counting. And having circuit representations mean you could reuse them for other things, or that you can design algorithms on the circuits that don't care about where they come from. So the idea is to replace that if you have two tasks on two settings, instead of doing one algorithm for each pair of setting and task, you can compile each setting to one circuit class and then design algorithms on the circuit class for both tasks. And you see that as 2 goes to infinity, the number of settings and tasks increases. You get, instead of quadratically many algorithms, you have linearly many algorithms. So that's better. Okay. So that's the philosophy of like using circuits as an intermediate representation for all sorts of problems. Let me define to you what are these circuits. Boolean circuit, I hope this isn't too exotic to you. So they're just a way to represent Boolean functions, or like a more concise way to represent Boolean formulas, except you can factor common sub-expressions as one gate. So it's a directed acyclic graph of nodes that we call gates. There is one specific gate, which is distinguished by being circled twice like this, which is the output gate, where we're going to read the value of the circuit. The inputs to the circuits are variable gates, so you can have multiple gates with the same variable if you want, and these we're going to plug in Boolean values in there. Then you have internal gates where you do a computation, so or, and not. The not gate has exactly one input, and it's doing the not of that input. The other gates here, they have several inputs, and it's doing the and and the or. I mean, I can have the constant 0 with an or gate with no inputs, and the constant 1 with an and gate with no inputs, because 0 and 1 are the neutral elements of the or and of the and operations. And what is the semantics of a circuit? So if I have a valuation mapping the variables of the circuits to 0 and 1, for instance, mapping x to 0 and y to 1, I will represent false as red and true as green. And I apologize if there are any colorblind people in the room, because I realize it might not be that clever. If x is false and y is true, this is the valuation, giving values to the variables. And then you can evaluate, call this an evaluation. So we will extend this to a function to all the gates of the circuits, giving them a Boolean value. We will do this following a topological sort of the circuit because it's acyclic. So the evaluation of a NOT gate is the other value than that of its input. The evaluation of an AND gate is the end of the evaluation of its input. But we'll get the story if you want to formalize this. And then the circuit returns a Boolean value, which is the value to which the output gate is mapped in the evaluation. And then recapping this in case this is news to someone, but I hope this is fairly intuitive. If you have questions, let me know. Okay. And so when can we compute these provenance circuits? So this is the general circuit, and now computing a circuit representing the Boolean provenance of a query on an instance. We've seen yesterday that so for unions of conjunctive queries, we can construct the Boolean provenance in p time. So the way I see it is like, from a theoretician's perspective, you do it in a very dumb way. You just think about all the possible, you have your query, you have the existentially, you have the disjuncts of the query, you treat them separately and you do a big disjunction. And for every CQ, you have the existentially quantified variable. You look at all the possible valuations, and if you find them in the database, then this gives you a conjunct. And you do the disjunction of all of this, and this gives you a Boolean provenance expression of the query as a disjunctive normal form expression. So a big disjunction of conjunctions. And in the conjunctions, you have as many variables as the number of atoms, or less than that. Okay. And this is a p-time process because the query is fixed. It's p-time in the database. No. I mean, the query can have, the query is fixed. So in the query, the fan-in is fixed. And in the database, the fan-in can be arbitrary, but then still I'm just testing out all possible valuations. So I don't care. I mean, once I have fixed the existential variables, I'm just getting ground facts that I can just read in my database to see if they're all here. And then if they are, I just take the conjunction of them. Okay. Disjunction of all matches. So if you think, I mean, this is a theoretician's answer. If you don't like p-time here and would like a more reasonable bound, there are classes of queries like acyclic conjunctive queries for which, so I think Nicole covered this. I'm not giving a definition, but so for some better behaved queries, you get better complexity bounds. And for more general queries like regular path queries that you've seen with Pablo, Datalog, You can still do this kind of thing. So for data log, which generalizes RPQs, you can compute the Boolean provenance in p time as a circuit. And this is where circuits are nice, because I think it's demonstrably false, maybe conditionally, that the same you wouldn't be able to do this with formulas. So here circuits bring you something. It's not that surprising, right? It's like if you have a query that does recursive things, it's going to reuse several parts of the database, and being able to factor together expressions makes things more pleasant. So we can compute the Boolean provenance of queries in reasonable formalisms. This isn't the hard part. We can even do so in practice. So this is a brief practical reminder of the existence of the real world in these slides, but don't worry, it's just that slide. We can, if you actually want to do these kind of provenance computations, let me advertise a tool by Pierre Senella, which is my former PhD advisor. This is ProbSQL, so it's an extension to the PostgreSQL database engine, a prominent open source database engine, where you can, on queries from a specific fragment of SQL, compute provenance annotations like this in arbitrary semirings, but in particular in the Boolean semiring, which are internally represented as circuits. So you can, this is, I mean, if you wanted to get, to evaluate a query and get the provenance value, you could do it with this tool, and then you could even export this circuit to feed it into something like a model counter to estimate or evaluate exactly the probability. So this is, I mean, it has limitations, but you can really run this. I've tested it, it works. I've used it in lab sessions, in classes, and so on. Okay. So this is the practice, and what I care about is that it's feasible in p time on the theoretically. So let's summarize what we've seen so far about provenance. We have fixed a Boolean query. Okay. We're given an input TID with probabilities. So this is like the provenance thing from before, except now we have probabilities. But for now, I forget about the probabilities. I just do a Boolean, I just compute a Boolean provenance circuit, which I can always do in p time. So this circuit, for instance. And now the key phenomenon is that the way the circuit, the semantics of the circuit, like it's true precisely on the subsets of facts where the query is true, tell me that, I mean, the inputs correspond to facts, so they have a probability corresponding to the probability of the corresponding fact. And a Boolean valuation of the circuit corresponds to a possible world of the database, but the same probability, right? The probability distribution in the possible worlds is the same as the probability distribution on the valuations of the circuits with the indicated probabilities. And a possible world here satisfies the query if and only if the valuation here makes the circuit true. That's the definition of provenance, right? This is definitionally guaranteed. So the modular idea is, how about we just take this and evaluate the probability of the circuit, forgetting entirely about the query, about the instance. Yes. To move to what? It could make sense to move to arithmetic circuits if you wanted to do arithmetic operations on the probabilities instead of Boolean operations on the possible worlds. And whether this is this has the same expressive power or not is the big open problem that I want to get you to. So that's a good point. Yes. Yeah. So we have, so forgetting about the input and just looking at this, so I will relabel these to be variables instead of facts because we don't care that they are facts actually. We now have a Boolean provenance circuit over the database facts. I mean, I switched examples, so it's not the same circuit anymore. Okay, so we have a Boolean circuit over the database facts. We have probabilities for the variables. And now the answer to probabilistic query evaluation is simply the probability that this circuit is true, right? So each variable has an independent probability of being true. What's the probability that the circuit evaluates to true? Well, unfortunately, this is intractable in general, right? Because if this is an arbitrary circuit, if I could compute tractably the probability that an arbitrary circuit is true, I could in particular know if that probability is greater than 0 and know whether the circuit is satisfiable. So in general, that's intractable. It's hard and sad, it's sharply hard, of course. But for this specific circuit, like this example is not completely random. It's an example chosen to argue that in some cases things go well. And why is this? It's because this AND gate is an AND gate of two variables that are different variables. And so the probability that it's true is the probability that this is true times the probability of this is true. The two are independent. generalizing this, if I have an AND gate where the inputs talk about different variables, like I can partition the variables over the different inputs, then its probability is just the probability of the inputs, the product of the probabilities of the inputs in that fashion. So here, and you see that's basically, I cannot generally transform this into an arithmetic circuit doing mathematical operations on the probabilities, but under some independence assumptions, I can do this. So here, with this assumption on the AND gate, the probability of the AND gate is just the product of the probability of the probabilities of the input. The NOT gate, where the NOT gate is always easy, the probability of this being false is 1 minus the probability that it's true, so duh. And then the OR gate, this OR gate is specifically interesting, and why is that? It's because its input are mutually exclusive. This input is true when X is false. This input to be true, X has to be true. So the two here cannot be true at the same time, and so the probability of this is the sum of these two probabilities. In general, that's not true, of course. I mean, be it only because if you do X or X or X or X, you cannot just sum the probabilities. They're going to go over 100%, and that's not good. But when the inputs are mutually exclusive, you can do that. And so in the specific case where the AND gates are independent in that sense and the OR gates are mutually exclusive, you can reinterpret the circuit as an arithmetic circuit on probabilities doing 1 minus, plus, and times. And then the probability computation is easy. And so what we're going to argue is that in the tractable cases, we can build circuits that satisfy these structural conditions. So to formalize these requirements give rise to the class of circuits with a very elegant name, DNNFs, for deterministic decomposable negation normal forms. And I mean, it's a very bad name, but unfortunately it's stuck, and it's especially bad because the D shouldn't be deterministic but unambiguous, but I will talk about this later. What are the requirements? So a circuit is in DNNF if the AND gates only have variables as inputs, and this is not a very interesting restriction actually, because for probability computations you don't care. It's just because these are defined as a class of negation normal form circuits where negations are applied to the variables directly. But for probability computations, you could get rid of this. So DNNFs is like the most common class, so I will nevertheless impose this restriction, and even though we know it's not very important. OR gates always have mutually exclusive inputs, so this means two inputs to an there is no valuation that makes two inputs of an OR gate simultaneously true. This is a semantic restriction, so it's not easy to check on the input circuit if that's correct, but there can be some syntactic ways of enforcing it. And AND gates are on independent inputs, which means that for an AND gate, there is no variable having a path to two different inputs of the AND gate. So like when I have an AND gate, the things that the inputs depend on are disjoint sets of variables. This is a syntactic restriction. And you could say, well, why define things this way? Couldn't this one be syntactic, this one semantic? Maybe there could be. So this is just one class of circuits. And the knowledge compilation people have been very industrious in coming up with all sorts of classes. So if you have other ways to define this, don't worry, they probably have a name, and there's probably some stuff known about them. And these restrictions make probability computation easy, just because, as I told you, the probability of a NOT gate is 1 minus the probability of its input, and that's always true, so you don't really need that. The probability of an OR gate, when the inputs are mutually exclusive, is the sum of the probabilities of its inputs. And the probabilities of an AND gate, when the inputs are independent, is the product. And these are, for the case of arity, 2 gates, but it generalizes to gates of arbitrary arity. Okay, so this is one of the many tractable classes of knowledge compilation. Small d, no, it's just part of the name. D means deterministic, the small d means deterministic, and the big D means decomposable. So this is a string. It's like an ugly string, but it's a fixed string. There is no. So let me show you and give you an idea. So I'm not going to go into the botanics of all of the possible classes, but just to give you ideas of the things that exist. There is a far more restricted class called read-once formulas. So these are Boolean formulas, not even circuits, where each variable occurs at most once. So like you can write the formula, and each variable has exactly one occurrence. This is also easy to compute the probability of, because when you have a formula in that way, the ands and the ors, by definition, they are on subformulas that do not share any variables, and so the ands are independent, and the ors are also independent, and so independent and an independent or is easy. You could convert these into DNNFs if you wanted. There are also classes defined like diagrams, for instance, OBDDs. I'm mostly mentioning this because you might have heard of OBDDs before. They fit into this picture, even though the formalism is different. So a decision diagram is something where you ask about the value of a variable, and depending on the value, you get to a different node. And then you have end nodes here telling you the answer is 0 or the answer is 1. So this looks pretty different from a circuit at first glance, but actually it's not that different. You could see a circuit as a generalization of this thing. So the direction is that this is easy to translate to a circuit. Circuits are not easy to convert back to this because circuits can do essentially conjunctions or disjunctions of separate formulas, where here it's more complicated. Anyway, so OBDDs means a decision diagram where the variables are ordered, meaning in any path from the starting nodes to the decision nodes, you will see the variables in the same order, and you cannot see the same variable twice. You have FBDDs, free binary decision diagrams, where you remove the orderedness restriction. And you have other classes than DD-NNF. So there is also DDs, where you remove the NNF requirement and allow arbitrary negation. So that's a generalization. And there are also subclasses like SDNNF, where the variables need to be split by the AND gates according to always the same partitioning. So there is a fixed tree partitioning the variables, and the AND gates always follow this tree. Or decision NNF, which looks a bit like a diagram, because disjunction gates are always deterministic, because they are saying basically either this variable is true and I do something, or this variable is false and I do something else. So you see that this guarantees that the two inputs to OR gates are mutually exclusive, and they look a bit like a diagram. Right? It's basically saying, well, I'm at an OR node, and either this is true and I go here, or this is false and I go here. So this connects a bit to diagrams, but in this case, you also have AND gates that you don't have here. Well, anyways, so this is from one of our papers. This is a diagram of the various classes that exist, just to argue that there are many classes. So this doesn't show you determinist DDs without NNFs, which would be a generalization of that. And read-once formulas would be a subclass of OBDDs, because they can be translated to OBDDs. So it's not a complete diagram, but well, to comment on this, so the higher layer is the class is our circuit classes, and the lower layers are the diagram classes. So here you have essentially conjunctions of independent things. Here you do not. And in these, so all of these classes are separated, and between the top and bottom layers, there is no exponential separation, because there is a quasi-polynomial encoding from the top classes to the bottom classes. And all of the other arrows correspond to exponential separations, and these mean removing, when you go here, you lose structure, so you can take variables in the order that you want, right here. And when you move in this way, you're losing, so here you have decision that guarantees that the OR gates are deterministic. And here you're losing determinism, and you have exponential separations always when you're going traveling through that route. So I don't want you to know all of the definition, but just to know that there is a vast landscape of tractable circuit classes. Another question becomes, if you have queries for which probabilistic query evaluation is tractable, can you understand the tractability in terms of getting a circuit falling into one of these classes, and which circuit classes do you get depending on the query? That's like a finer notion of tractability. You can have a tractable probability computation because you fall in one of these tractable classes, and you have to figure out which one. So what's known? So for self-join free CQs, the story is pretty easy. Given a hierarchical self-join free CQ and a TID, we can compute a read-once formula. So that was the most restricted class of the previous slide. We can basically write down the provenance, the Boolean provenance in linear time as a read-once formula. And this gives you in particular the tractability of probabilistic computation. To do this, you just follow the algorithm that I showed you, right, about the stars and stuff, and you observe that it was just doing independent ANDs and independent ORs of disjoint probabilistic events. So if you just write down this as a Boolean formula, you will get something of linear size, but you have like the facts of the database separated by ands and ors, and that's a read-once formula. And this explains that you can compute the probability. So I told you this would be a bit disappointing because we're not learning anything new in terms of probability computation. We're just saying, well, this algorithm is actually computing a read-once expression and evaluating it all in one go. But that's I think is a bit enlightening because you can see this as first doing a symbolic provenance computation, and then you can probably use this computation for other things, but you can also compute the probability of the provenance expression. And so from this we recover the linear time, the tractability of policy correlation. In fact, it's in linear time up to the cost of arithmetic operations. So assuming that the arithmetic operations on the probabilities stay constant time, which is more or less reasonable depending on your model. And I don't want to get into the details of computational models. Okay. So case closed for self-join-free CQs. Fortunately, the case of UCQs is more interesting. Unfortunately, I didn't give you the details about the UCQ algorithm. So I just want to point to you that there are results known in this area, and there is a big open problem that's lurking. So for unions of conjunctive queries, probabilistic reevaluation for unions of conjunctive queries, we have a dichotomy on the complexity of the problem, but what do we know in terms of provenance representations and tractability of the intentional approach? Well, there is a characterization of the queries for which we can compute read-once provenance expressions. So in the self-join-free CQ case, read-once expressions covered all of the tractable cases. For UCQs, they cover some of the tractable cases, but not all of them. There is a characterization of the queries for which we can compute OBDD provenance. So OBDD is more general than read-once. So these classes are different. There are some queries for which you get read-once expressions, some queries for which you get OBDDs, but no read-once expressions. And there are some sufficient conditions known to guarantee having a lineage as an FBDD or as a DDNNF. But these are not characterizations, these are sufficient conditions. So in this paper, they say, well, if this happens, we can get an FBDD. If this happens, we can get a DDNNF. And then the question is, can we characterize, and what's like, for the tractable UCQs, is there a circuit lineage in which we always fall? So we already know that from some fairly recent papers, it's known that there are some tractable UCQs, so some UCQs for which probabilistic computation is tractable, but there is no tractable, I mean, you cannot compute in p time a representation of the lineage as something called the DLDD, which is a generalization of decision DNNF. So it covers one of the subclasses of DNNF. So we know like decision DNNFs is not enough to get tractability. It is known that the SDNNFs, so structured DNNFs, are not sufficient either. So if you impose structuredness, it doesn't work. If you impose decision, it doesn't work. And it is not known if you can do it with DDNNF. So in the 2013 paper, basically the message was, these are sufficient conditions for DDNNFs, but we think not all queries can be handled in that way. They even conjectured that a certain query did not have any DDNNFs. And so basically the message was, we have a super algorithm that covers all the tractable cases, but you won't be able to capture them via circuits. Because they say the intentional approach, it's modular, but it's more crude because you forget about the query when you see the circuit class. So they were thinking, this algorithm is so complicated, it really needs to know the details of the query. You won't be able to see its tractability in terms of circuits. So this paper conjectures the query Q9, it was called, doesn't have tractable lineage representations as a DDNNF. And then lately, in 2020, and like following discussions with other people, including Guy van den Broek, Michael Monet, former PhD student of mine, said, well, query Q9 actually has a lineage representation in a tractable class. And so we need another counterexample, and we're a bit running out of counterexamples. So it's all of this is pretty much open. So we don't. So the good candidates to get tractability would be DDs, so DDNNFs, as I presented to you before, allowing arbitrary negations in the circuit, because why not? Then you can still compute probabilities. It is open whether these two classes are different, because it is open without whether the DDNNFs that I presented to you are closed under arbitrary negation or not. So by closed, I mean, DDNNFs can represent any Boolean function. What I mean is if you have a DDNNF and you want to take its complement, can you polynomially compute a DDNF representation of the complement? That's open. We don't know. Because it's not going to preserve the determinism requirement, I think. So, I mean, in terms of in logical terms, you can do this, but since you have these restrictions of determinism, decomposability, and they're not interchangeable, right? So, I mean, if you take a decomposable AND node and it becomes an OR node, then it's not going to be. So, this is supposed to be a hard question. So, unfortunately, you cannot solve it in this way because it's just reasonable. It's a reasonable question, but it's not as easy. So we don't know whether these two are separate. In that paper, Michael Monet gives examples of things having a DD which are not known to have a DDNNF. It's not clear from that paper whether having just one negation at the top is enough or whether you would need multiple negations in all places. And we don't currently have a good conjecture. So the problem is that the query is not having these kind of representations. Q9 is already very complicated. And the more you continue, the more the counterexamples would look scary and not very enlightening. So it's not easy to come up with counterexamples. So the crucial question, I think this is a very interesting open problem, but I'm having a hard time explaining exactly why. I mean, I would like to get this problem into a form where I can go to people not knowing probabilities and tell them that this is a question about circuits. The key question is a bit related to the question of Arnaud Durand earlier, is you have this Boolean computation of a provenance, and you have a tractable algorithm that does inclusion-exclusion. So it's computing numerical probabilities, and then it's messing them up in using arithmetic formulas like 2 times this probability minus 4 times that one plus 6 times that one, and then magically going back to the probability of something that's the correct answer. This is not something that you can do in a Boolean circuit, because in a Boolean circuit, you cannot subtract nodes, you cannot subtract probabilities. And so the question is really, is it more powerful to do these arithmetic computations directly on the probability, on the probabilities, or can you see them as a way of doing Boolean expressions? And it's also, it's related to question also about if you take an inclusion-exclusion formula, can you reorder the terms so that you only stay in the realm of probabilities and don't go below 0 or above 1? So I think it's a very fundamental question. I haven't formalized it, but yeah.
Have there been attempts to reduce some hard complexity questions?
Hard complexity questions.
For instance, the differences. There's some interesting complexity questions with the differences between monotonic circuits and general circuits.
But the thing is, we have negation, so the circuits are not monotone. But it's, I mean, what's challenging with inclusion-exclusion is that we do subtraction. And you see that negation allows us to do, basically having a NOT gate allows us to subtract probability by doing 1 minus something, but it's not allowing us to do 4 times this minus 5 times that. And the question is whether we can build gadgets with plus, times, and 1 minus, while respecting the independence and the mutually exclusive restrictions to do the same numerical computations that could happen in an inclusion-exclusion formula, right? So yeah, I mean, it would be nice to have a characterization of the tractable queries in terms of circuits, but yeah, we don't have one yet, unfortunately. Okay. Do you have questions about this? Okay, so if not, we have time to talk about not this. We have time to talk about width-based approaches and tree width and all. So for those of you who like probabilistic graphical models, we're going to use the same width measures that guarantee tractability. So you might have heard about, say, bounded tree width-based networks and message passing algorithms. So this is our way of seeing this in the world of probabilistic databases. As saying if the database has bounded tree width, then we can evaluate queries and we can do probability computations efficiently. And we can see this also via the circuit classes that I presented to you before. So, okay, so probabilistic reevaluation is intractable for essentially all queries. And what can we do? We can restrict the database. We can restrict the structure of instances. So you see, basically what I'm trying to do here is we have this depressing message about queries. Well, some queries are tractable, but most queries are hard. But this is on arbitrary databases, right? So what if my database wasn't that bad, and my database had some satisfied some structural conditions, making the problem easier? So in practice, it could be the case that the database has bounded through it. I mean, I don't know how often this happens in practice. And well, from an experimental study by Pierre and others, it looks like it doesn't happen that often. But at least on theoretical terms, it might, right? And this is also going to connect us back to results about the tractability of query evaluation on words, trees, and bounded tree width structures. And basically saying we can extend these to also cover, also do probability computations. Right. So the results, I mean, so here I'm starting to present results that are my own. So I have put the pictures of the people with whom I have done them. So the result is if you have queries that are very expressive, so all UCQs, any CQ, any UCQ, but even any monadic second order query, if you run it on a TID instance whose tree width is bounded by a constant that you fixed beforehand, then probabilistic reevaluation is tractable. And there is a converse, but it has some like intuitively you would want to say if you don't bound the tree width, then it's intractable. And we show something like that, but with significant limitations, and I will explain. So okay, I'm going to present mostly the upper bound of this result, and I'm going to do this in steps, which will be a way to like reacquaint you with things you should be familiar with, like word automata. So Pablo has presented to you word automata. I'm not sure if anyone's presented to you tree automata, but I'm going to define tree automata, and then I will sketch tree width. Okay, so word automata and probabilistic reevaluation on words. When I have words, so I'm now moving to a weird database setting where my database is a word, and the facts of the database tell me what's the color of every node. So this is very much fantasy land. It's very far removed from practice. But why not see the evaluation of an automaton on a word as a query evaluation problem? So the database is a word with colors. The query is something in monadic second order logic. So a CQ would be something like I have a red node and then a blue node and then a green node or whatever. I'm allowing much more expressive queries. Well, this is a query that's still a CQ. Is there a pink node and is there a blue node? But I could allow monadic second order queries. I will explain in the next slide what monadic second order is, so don't worry. You can also see this as just having a word automaton because it's the same expressive power. And then the result is true or false, depending on whether the word satisfies the query or not. So here, like I'm doing things really stepwise. So this is evaluating a query on a word without any probabilities. And this is just a fancy way of saying I want to run an automaton over a word. So I'm studying the complexity in data complexity. So the query is fixed and the input is the word. And what is this monadic second order query language? So you can think of it as a word automaton, or in terms of logical operations that are allowed, the allowed operations are checking like atoms that talk about the color of nodes. So something that said node X is blue, node X is red or whatever. Something that says there is X is a position and Y is the next position in the word. So X and Y are two adjacent positions in that order. And then and or and not, so Boolean combinations of these. So for instance, you could say node X is pink and node Y is blue. And then you have first order logic, so you can quantify existentially and universally. So you could say there is a pink node and there is a blue node. And then you don't just have first order logic, but you also have monadic second order logic, so you can quantify over sets of elements. And in particular, this allows you to talk about the transitive closure. So you can say X is before Y at an arbitrary distance in the word, like there's an X and there's a Y, and one is before the other, but we don't know how far. This is something that you could not do with first order logic with successor, but that you can do with monadic second order logic. And you can thus express, for instance, for every pink node, there is a blue node which is after the pink node. Okay. So that's the query language. And it's known that this is actually a logical way of presenting automata, and specifically deterministic automata. So a deterministic word automaton. So if I fix an alphabet and I have a word, I can define an automaton by saying I have states, and I have some final states, and I have an initial state, which I present as an initial function, giving me the state at which I land after having read the first letter. Okay. So, I mean, I guess you're all familiar with automata. Let me just like introduce the formalism like this, because then I will show you three automata and you will see why I did it like that. So for this query, checking if there is a pink node and a blue node, the initial function, so I have four states, meaning I haven't seen any color, I have seen blue, I have seen pink, and I have seen both. The final state is I have seen both. So if at the end of the word I have seen both colors, then I return true. And the initial function is, well, if my initial node is white, then I haven't seen anything. If my initial node is pink, I have seen pink. And if my initial node is blue, then I have seen blue. And so the automaton starts at state bottom, no color seen. And then I have a transition function telling me from one state and one node color, what is the state to which I go. So if I have seen no color and I see a pink node, then I have seen the pink color. If I had seen the pink color and I see a blue node, then I have seen both colors. If I have seen both colors and I see some node of whatever color, then I have seen both colors. And this allows me to evaluate the automaton over the word. And we can check then if at the end we get the final state or not, and then the automaton accepts or rejects. And you see that the semantics of this automaton is equivalent to the semantics of this query. Right? Okay. So it's known from the 60s that monadic second order and word automata have the same expressive power on words. And so query evaluate. So if I fix an NSO query, I can evaluate it in linear time in the input word in data complexity by translating it, which might be complicated, but it's a constant to a deterministic automaton, and then running the deterministic automaton over the word. Okay. This is non-probabilistic query evaluation over words. Now let's talk about non-probabilistic query evaluation over trees. And this is the same thing with monadic second order logic, except that the arrow now means X is the parent of Y instead of X is the predecessor of Y. So this is like a word, but which can branch, okay? And yes or no, and the query result is yes or no, is the query true or false in the tree. And monadic second order or trees turns out to be equivalent to tree automata. So these are just like word automata, except that they work on trees. And I'm going to present bottom-up deterministic tree automata. So this is like a word automaton running from the bottom of the tree to the top, except that when I'm at a node here, the states that I get to depends on the label of the node and on the states of the two child nodes. Two child nodes, it's not just one. So for the same query as they're both a pink and a blue node, the states are the same states, the final states, the same final states, the initial function is the same. What changes, and so this, I can evaluate, my automaton is at a state at every node of the tree, and I can initialize it on the leaves with the initial function. So just like a word automaton, except I start at every leaf. Another transition function is something like, given the states of two children and the label of a node, to which states do I go? So if I have on this subtree, I had seen a pink node, and here I hadn't seen anything, and I'm at a pink node, then I have seen a pink node in that subtree. If I had seen a pink node in this subtree, a blue node in this subtree, and this node is of whatever color, then I have seen both colors on that subtree. If I hadn't seen anything and I have a node without a color, then I still haven't seen anything. So I didn't write down all of the transitions. But with these transitions, these are basically the building blocks to evaluate the automaton bottom up and get to a state here, which is the final state, and which is the state of the root, sorry. And if this is a final state, then the automaton says yes. Otherwise, the automaton says no. I'm doing this a bit quickly. I hope that, like, did someone get confused about these three automata? Or so if you know word automata, really, I've presented things to you in this way so that you can really think of these as just a weird form of word automata, where the word is a kind of branching thing, and you have runs that meet. And so at a node, you don't just base your state on the label on the previous node, on the previous state, but on the previous states of the two children. Yeah. And it's known that MSO and tree automata have the same expressive power on trees, same thing as words. So query evaluation of MSO over trees is in linear time by translating to a deterministic bottom-up tree automata. So now let's add the probabilities and see what does it mean to do probabilistic query evaluation over trees. So the database is a tree, but it's like a TID in the sense that I have some probabilistic facts. And to me, the right framework, and the one that will work for tree width afterwards, is to say the nodes either have a default color, which is white, or they have a color and a probability of keeping that color or of having no color. So this means this node has 80% probability of being pink and 20% of being white. This one has 20% of being pink, 80% of being white. This node has 60% probability of being blue, 40% probability of being white. So because I don't want the tree structure to change depending on my probabilistic draws, the TID aspect is on node colors that can either be here or not be here, but the nodes are always here, the structure never changes, okay? And the draws are independent across the various nodes. The query is a query in monadic second order logic. Remember that the query never talks about the probabilities, so this is the same query as before, expecting to be run on a deterministic tree. And what I want to compute is no longer a yes or no answer, but it's a probability. I want to know what's the probability that my probabilistic tree here satisfies the query true. So what's the probability of drawing according to this distribution a tree that will have both a pink and a blue node? Okay. So this is the problem, and we're fixing again in data complexity. We're fixing the query and getting as input a TID. And the results that we're going to show is for any fixed MSO query, the problem. The probabilistic query evaluation problem in that sense is in linear time, assuming that arithmetic operations take constant time. I didn't put my name next to this result because, well, first, it's not a very complicated result, and second, there was a paper on running tree automata on probabilistic XML documents that pretty much did this, but presenting it as probabilistic XML and stuff. So this is a somewhat different presentation of it, to not have XML vocabulary and to make tree encodings work afterwards. But this, I mean, you will see it's not a very, and if you're still awake and you're not too tired by what I'm telling you, you could try improving this in your head and saying, well, this is a tree automaton that works bottom up. I can think about the probability of being at a given state at a given node, and then I can just compute this at a kind of dynamic programming way and get to the probability of the final state. And that's just basically what I'm going to do, except I'm going to make it sound more complicated by introducing circuit classes, right? But it's not a very difficult result, actually. So, I mean, that's the dynamic algorithm. I'm going to present it to you in terms of Boolean provenance and Boolean circuits so that we can use what we saw before and have these circuits, which it turns out are also useful for other classes. I mean, I could say speculatively, doing things via circuit is so much better because it's modular. You could use it for all sorts of different problems. But this is a true story in the sense that during my PhD, I did this with I did this first without circuits for probabilistic evaluation. Then I realized I could do it via circuits, and I thought, oh, that's nice. DDNNFs, okay, they show up, nice. And then it turns out that you can use the DDNNFs for enumeration, and we showed enumeration algorithms on trees using the exact same circuits. And this circuit-based approach for enumeration brought new results to this enumeration problem of MSO on trees that had been previously studied. So, I mean, this motivation of doing things in a modular way, it's not just speculation, it can really help, right? So let's do the same thing as we did before by introducing provenance and defining provenance on trees. And it's exactly what you would expect, right? We're going to talk about variables corresponding to the tree nodes that have a color and saying these nodes can keep their color or not. So if I have this valuation that maps the nodes 2, 3, and 7 to 1 and the others to 0, it's saying these three nodes keep their colors. The other nodes, they don't, but they don't even have a color, so that's okay. And the valuation where only node 2 keeps its color gives you this tree. If 2 and 7 keep their color, it gives you this tree, and so on, right? And so if you have a query, is there both a pink and a blue node? You can think about what are the valuations for which the queries choose. There's like all the subsets of tree facts, but the tree structure is fixed. It's just the colors that are changing. So on this valuation, the query returns yes. So on this valuation of the tree, there is both a pink and a blue node. On this valuation, the query returns no, there is no blue node. This valuation, the query returns yes, there is both a pink and a blue node. And so we can talk about the Boolean provenance of the query over trees as a function of the color of the nodes, right? As a function of these variables telling me of which nodes do I keep the color. So this tree, if I ask, is there both a pink and a blue node? The provenance circuit would be like this, yes? Ranked alphabet. So I'm assuming that the tree is binary, if that's your question. Okay, so it's a full, okay, yeah, I didn't make it very formal. So it's a full binary tree. The nodes that are not leaves are internal nodes that have exactly 2 children, which are ordered, like I can distinguish, but it doesn't really matter, but let's say they're ordered a bit simpler. And the nodes have this color, which can disappear. But for now, so I don't have the probabilities. I'm just thinking I have a tree with colors. I'm just imagining what if the colors were to disappear, and I'm just writing a Boolean function, like a Boolean circuit, describing for which colors do I need to keep, which node colors, not the colors, the nodes, for which nodes do I need to keep the color so that the query is true. Okay, I hope that's clear. Huh? So here you see, if I want to have both a pink and a blue node, I need to keep the node 7 because it's the only blue node, and I need to keep the nodes 2 and 3 because they are the pink nodes. Right? So formally, yes, you have a query, you have an uncertain tree, and we're defining a circuit where the variable gates correspond to the tree nodes instead of the database facts. And the condition is that for any valuation, Boolean valuation of the tree nodes, describing which colors, which nodes keep their colors and their color and which ones do not, then the circuit evaluates to true precisely on the valuations where the corresponding tree satisfies the query. Right. And so here is the key result. Some gaps will be filled. For any bottom-up tree automaton, so the automata we've been talking about, on an input tree, intractable combined complexity. So if I'm given the automaton, so if I were given the MSO formula, forget it. The transition to automata has bad complexity. But if I'm given the automaton, I can do basically it's doing an automaton product and seeing it as a circuit, which is exactly what you would do in the dynamic algorithm. So the dynamic algorithm that says, let's think about the probability of each automaton state at each node is just doing a product. And here I will be doing a product as a circuit, and I will talk about the probability, the properties of the circuit. So given a tree automaton and a tree, I can build a provenance circuit of the automaton on the tree, intractable combined complexity. And the circuit falls into this weird SDNNF class. So let me just show you what the circuit looks like. So if this is my alphabet, this is the automaton for, is there both a pink and a blue node? It has these states, and we've discussed this automaton before. On this, it's an inductive construction, right? We do it inductively. On an internal node that's blue like this, and on every node, I will have one circuit gate corresponding to each automaton state, which will be an OR gate. And I have one variable gate of the circuit corresponding to that node. This is where we're going to read whether we have kept the blue color or not. And now we just wire together the transition. So when I have a transition like this, that tells me from state P and state bottom, and if I have a blue node, I get to state T. I wire this up by saying, well, if this is true, so the semantics of this gate is that the gate is true if the automaton can be at state P on this node. And if this one is true, then this end is going to be true. And I also take the end with this to say, I need to read a blue label, so I need this to have kept its color. And I feed this into the gate for the target state on that node, okay? So this is materializing the possibility of doing this transition when I have kept this node and when I have I can be at the right states of the two children. And I also need to wire up the transition for when I have not kept this the color of this node. Even if this is a white node, I can still combine together states. And here I'm saying, well, if I am at state P here and at state bottom here and I read nothing,
then I'm at state P here. So it means I'm at state P on this on this node. I'm at state bottom on this node, and I don't have this node. Then I can get to state this one. So I don't read this node, so I get to state P. So this is really just an automaton product, huh? And this is clearly in this complexity, and the invariant. You show correctness of this by showing the invariant that on every subtree at every node for any state, the corresponding gate here can evaluate to true if the automaton can reach this this state on the. For a tree valuation, the gate evaluates to true if on the gate evaluates to true under that valuation if on the corresponding tree the automaton can get to this state. And it turns out that if the automaton is deterministic, or even if it is unambiguous, then the circuit is also deterministic, intuitively, because the automaton can only, on one fixed valuation of the tree, the automaton only gets to one of these states here. And so it's not possible that, that there's only one transition that can fire depending on the value here. And so it's mutually, the OR gates are mutually exclusive. This is why, but even without this construction, it shows you that the determinism here, that means the two inputs of an OR gate cannot be true at the same time, is really an unambiguity requirement. It's not that I can determine which one it will be that will be true, is that I cannot have two that are true simultaneously. So you don't know the formal definitions of this. I'm not going to formally verify that this satisfies, because I guess everyone's forgotten the definition of DD&NF already. But these problem circuits, they are DNNFs because negations only happen at the leaves. The conjunctions, they talk about disjoint subtree. So you see this conjunction is between this node and a conjunction which is between the left subtree and the right subtree. So I'm always partitioning the variables in a fixed way, and this is why I'm structured. The partitioning follows the shape of the tree. When the input automaton is unambiguous, it's a deterministic SDNNF. The width of what's called the width of the formula corresponds to the number of automaton states. And as a small aside, if I had done this on words instead of trees, the circuit that I have, I can see it as a diagram, like an OBDD. So the reason why I have not a diagram but a DDNF is because I'm on a tree and I'm doing these ends, right? And so this gives me the result I had claimed before, that probabilistic evaluation of MSO on probabilistic trees is in linear time. Okay, so there's not much time left. So we have seen this on trees, and now let's go back to the world of databases. But if we have a database that looks like a tree, could we adapt the same approach? Unfortunately, there is a structural parameter of databases that is called tree width that allows us to do precisely that. So I'm going to define tree width at an intuitive level and say, if you have a tree, what is a tree? Really? A tree is something where you can take an edge and then you can decompose the tree by talking about the incident edges to the edge you've selected, and then recursively decompose based on these edges. And the parts that you decompose in this way are separate, like there's no additional thing connecting them here because this would be a cycle. And this is the way of seeing a tree. If you have a graph which is not a tree, you could maybe do the same thing, but instead of taking an edge, you could take a small subset of vertices, for instance this, and then you could decompose with other subsets that overlap with the subset you selected, and the decompositions, like the rest of the graph would only touch one of these separators, and you wouldn't have something like this. So maybe like this graph, it's not a tree, but I can decompose it with triples of vertices instead of pairs, instead of edges, and have this same kind of recursive decomposition. Well, that's tree width. And the tree width is how many vertices do you need to take in a subset to be able to decompose the tree in that fashion, basically. So it's like a tree, but there's a bit more vertices at every level. So trees have tree width 1, cycles have tree width 2, and graphs with high tree width are cliques, but also like sparse graphs, sparse planar graphs like grids can have high tree width. And tree-like means the tree width is bounded by a constant, and it's already known by something called Courcelles theorem from 1990, that if you have an MSO query on tree-like data, so data of bounded tree width, there is a way to transform this to a tree automaton and to transform the data into a tree using the so-called tree encoding, so that you can evaluate the automaton over the tree and get the query answer. And so you can evaluate the MSO query over tree-like data in linear time. So MSO over trees is linear time. MSO over tree-like data is also linear time by this result. And what is true, what we know about what we've shown about probabilistic evaluation is that if you do the same thing, but instead here you have probabilistic tree-like data. So this is, I mean, I've drawn this like a bit in this way, but this is really a TID database where the what's called the Geifman graph, so the hypergraph of the database has bounded tree width. Then we can do the same thing of transforming to a tree automaton, transforming this to a tree encoding, which is now probabilistic in that the nodes have some probability of keeping their colors the way I've explained. So that when we evaluate the tree automaton on the probabilistic tree encoding, instead of doing directly the evaluation, we do this circuit construction in linear time, well, in time this times this. And then from this circuit, as it's in a tractable class, we can get the probability and we can do the evaluation and we can get the results that I promised to you, so that we can do probabilistic query evaluation of a query on the bounded tree width database in linear time complexity, assuming constant arithmetics, that arithmetic operations take constant time. And well, there is a lower bound to this that I'm not going to go into. So basically we say, if we restrict to graphs, so arity2 signatures, there is a query which is intractable for probabilistic computation, so sharply hard on any family, no matter how you restrict the input instances, provided the restriction doesn't limit the tree width and that you can efficiently construct high tree width graphs in the family. So like several limitations to this result, but I will skip them. Okay, so I will skip everything I could tell you about other things and jump to the conclusion. So what have we seen together today? We've seen the main probabilistic database model, tuple-independent databases, tags have independent probabilities. We also saw BIDs and PC tables as more expressive models. We've seen the probabilistic query evaluation problem over probabilistic databases, specifically TIDs, and leading to a theoretical question: for which queries is probabilistic query evaluation exactly tractable? I've shown to you the Dalvi and Suciu dichotomy on self-join free CQs and hinted at its extension for UCQs. So self-join free CQs, it's precisely the hierarchical queries that are tractable. And for UCQs, there is a more complicated dichotomy. I've explained to you how this tractability result for self-join free CQs could be explained in terms of read-once formulas and DD&NF circuits, and pointed at the problem, which is open, of whether the same is true for UCQs. And I've explained to you why if you bound the instance to have bounded tree width, you can have tractability of UCQ, of all UCQs, but even of monadic second-order logic. Okay, and there are some extensions that I didn't have time to talk about. In terms of other topics of research, so there is research about more general query classes. Here's a summary by Dan Suciu at PODS 2020. Recently, there have been, by some people in the room, extensions. So in 2021 to probabilistic databases with infinite domains, probabilistic databases that can be updated, open world probabilistic databases, active probabilistic databases, and so on. Maybe there are other extensions that I'm not aware of. And there are like several open questions, I think, so about how do these techniques connect to different tasks like repairs that Jeff will talk about, shapelet values that Benny will talk about, graphical models, and so on. How do these theoretical questions about dichotomies relate to more theoretical domains like the CSP problem and variants of the CSP problem? Can all of this be implemented in practice? So there's ProbSQL, but could you extend it to support what you really need in practice, like aggregates and such? Can you do approximations, and can you use these in practice? What are for the connections to knowledge compilation? Do the tractable circuit classes cover all of the tractable query classes? And I've told you this is open. And something that I'm currently discussing with Michael Monet, we have a query-based approach for tractability, saying the safe UCQs are tractable, the other ones are hard if you allow arbitrary databases. We have an instance-based criterion saying if the instance is bounded true width, then everything's tractable, otherwise it can be hard. But we're missing an understanding of when do we have tractability for a given instance in a given query, like mixing tractability on the query and tractability on the instance, but we don't have a combined criterion for tractability, and I think it would be interesting to have that. I'm sorry for going a little bit over time, and I hope we still have a bit of time for questions. Thanks a lot for listening to me.